stage. For this session, we have with us Dr. Munish Bhatia. Dr. Bhatia is presently serving as Assistant Professor at NIT Kurukshetra. He has earlier served as Project Engineer Scientist at School of Computing and Electrical Engineering IIT Mandi. He did his Masters and PhD in Computer Science and Engineering from GNDU Amritsar. He has more than 5 years of teaching experience and more than 7 years of research experience. He is a highly motivated researcher with expertise in IoT applications, data analytics, deep learning, and cloud and fog computing. His research areas also include cloud computing techniques for optimization. He has also done project on quantum computing inspired vehicular route optimization for industrial applications sponsored by Government of India. He has number of publications in reputed journals and conferences. Talking about his awards, he has qualified UGC NET in Computer Science and Engineering twice and GATE in Computer Science for 4 times. He is also indexed in top 2% scientist as per Stanford University, USA in 2022 and 23. It's such a great honor to have you as sir here with us. I'm sure our participants are going to learn a lot. So please take the stand and please. Thank you so much.
First of all, I would like to thank Dr. Ravinder for inviting me here, and it's such an honor to be here with you among all of you. And I'm sure what I'm going to present today will be, helpful to you, especially for your students. And as I'm told that this is the first 5th day of the workshop, and I'm sure you are familiarized with the concept of quantum computing before the last 4 days. As for my presentation, as you can see here, we are talking about the quantum computing, which is the next generation computing paradigm. Now, when we say next generation computing paradigm, it means that our traditional computing systems, the computers that works upon electricity, that works upon transistors, integrated circuits, that will be obsolete. That means once the quantum computing revolution is there, we will be, basically transforming the way we are, performing computing, the way we are using computing powers. Now, as for my presentation, as you can see, I have basically confined my presentation starting from the introductory part, then talking about the quantum mechanics, because quantum mechanics is the core concept why the quantum computing has developed. Then talking about the architecture, working principles of quantum computing, and how quantum computing is different from deep learning. We are talking about the artificial intelligence nowadays. Artificial intelligence, then we talk about the machine learning, deep learning aspects. So if we are talking about deep learning, we are saying that it is a very, highly computing intensive task that we are performing in deep learning environment. But if we are talking about the quantum computing, it is a step further than the deep learning. How that will be learning today. Then I will talk about one of the case study. It is more specifically research papers. It is my research paper that has been published in IEEE IoT. It in the SCA in the journal with more than 10 impact factor. So it is focusing on how quantum computing can be used for IoT applications or IoT networks. Then talking about some of the applications of quantum computing, where we can use quantum computing, then what are the challenges and what is the future scope. So let's talk about the introduction first. Now I hope everyone is familiarized with the concept of quantum computing. Still I am going to let you revise what is basics of quantum computing. So it is a type of computing that uses quantum mechanical phenomena such as superposition and entanglement. Now these two keywords are very important when we talk about the quantum computing, because everything that quantum computing provides you is these two phenomena have basically resulted in that. So let me ask you, since it is the 5th day, so I hope you are familiar with the concept of superposition. Anyone who can tell me what is the superposition?
So there's 0 and 1
at the same time.
Yes, that means simultaneous existence of zeros and ones, right? we say simultaneous existence, that means at the same instance of time we can have 0 as well as 1. And the how we can distinguish between 0 and 1, it is based upon the probability. Okay, what is the probability of a system to be in a 0 state, then it is a 1 state. And we can represent this simultaneous state using Dirac's equation. Okay, so we'll talk about that later on. Now the second keyword is entanglement. So what is entanglement? What is entanglement?
So if one bit is changing at one place, the information at some other place will change according to that. Like a bell state.
Yeah, bell state is there. In other words, what is entanglement basically? If we say that the two states are entangled, are basically mapped to each other. If, let's suppose, I'll give you one example here. If a entire system is stable, okay, and if a rotation of one of a particle in that is, let's suppose, anti-clockwise. So in order to make an entire system stable, what will be the rotation of another particle? If there are two particles, one is rotating anti-clockwise, entire system is in stable state, what will be the rotation of another particle? Clockwise. So that's entanglement. That means knowing the state of one particle, we can get the information of another particle. Okay, so that is entanglement basically. Then, unlike classical computers, we use that use binary digits or bits to represent information. Quantum computers use qubits. Okay, the qubit concept is there that can exist in multiple states at the same time. This allows for the quantum computers to perform certain calculations much faster than the classical computing. Now, in classical computing, we have certain problems which are basically known as NP problems. Okay, I'm sure you are familiar with the concept of P class and NP class. Everyone? NP hard. What are NP hard problems?
Complexity is exponential.
Complexity is exponential. Okay, and any other detailed explanation other than exponential complexity? I mean, how can you identify whether a problem is NP hard?
The solution is exponentially. It is exponentially hard to calculate the solution, but verifying can be done in polynomial time.
Yes, that was the keyword I was looking for. That you cannot identify the solution in polynomial time. Okay. So, such problems, very basic problems of, for example, I am going to take is the traveling salesman problem. This is a fundamental problem, which is an NP problem. Okay. You cannot basically solve a traveling salesman problem in deterministic time. Complexity is, I think, 2 raised to power n, if I am not wrong. So, such kind of problems, if we have the quantum computing with us, we can solve that in minutes or in seconds, basically. Why? Because we are able to map different solutions in the entire solution space at the same time. We can solve different states, different solutions. We can traverse different paths at the same time, so that we can identify which is the shortest path possible in that. So, quantum computing will basically sort of transform all these classical algorithms all together. One more example I would like to give here. In our credit card or debit card system, we have AES security. Okay, some sports 128 bits, some sports 256 bit security is there. Okay, anyone who is of security experts, security, cloud security or cyber security? Go ahead. I mean, who is familiar with cyber security concepts? Anyone? Okay. What happens in a credit card? We are having a security system, to secure the details of the credit card or debit card. So that is basically 256 key cryptography. So that means number of possible combination are 2 raised to power 256. So that is very difficult to break as for the classical computer. But when we are having quantum computers, it can break that crypto system in seconds. So once quantum computer is there, and our banking system has to change. The security of the banking system has to, transform altogether. Then talking about the brief history. As you can see here, different scientists, worked for the quantum computers starting from 1982. Feynman proposed the idea of creating machines that are based on the laws of quantum mechanics. Then 1985, David developed the quantum Turing machine. 1994, Peter Shor came up with the quantum algorithm. Now this was one of the main, say innovation or novelty that was there, that Peter Shore presented in 1994 about breaking or basically factorizing a polynomial or factorizing a large number, because this is one of the base of breaking the cybersecurity protocol. Why? Because the advanced encryption standards, the RSA protocol, these are based on the mathematical, prime numbers. You take the prime numbers, something like that is there. But this algorithm is able to detect those prime numbers very easily. So again, benefits of quantum algorithm are there. Then Grover Dove's quantum search algorithm with the, you can say, complexity order of square root of n. We are having different search algorithms: linear search, binary search, heap sort and heap search, and number of searching algorithms are there. So what is the best complexity in searching algorithms? Order of n. If I let's talk a linear search, what it takes order of n time. So if I have an algorithm that computes or that perform a search in order square root n, so it will be better, obviously. So again, certain advantage of that. But the concept of quantum computing has not, it's not a recent concept. As I say, the major advancement started from 1982. But the concept was there, was theorized in starting from 1900s. You can see here, initially, Planck, Max Planck was there that proposed quantum hypothesis. Then EPR paradox, Bell's inequality, work for quantum information theory, and so on. Within passing of the time, you can say the entire, now we are at the ongoing advancement where different companies like Google, IBM, IonQ, different are able to basically stabilize the qubits. They are able to, they have basically presented the quantum computers that can support up to more than 5,000 qubits. Okay, so you can see the timeline here. Then why quantum computing is important? Now we are talking about this buzzword, quantum computing and all together. Why it is so much required nowadays? Why it is a need to study this? Okay, quantum computing is a new paradigm and it is based on quantum mechanics. But why it is important? Why we are studying this? In fact, you can see different applications which it support, which I already discussed earlier. But to be specific, quantum computers play a major role in cryptography. Okay, we are having it is a notion that security is never 100%. No security is 100%. There is always a loophole in that. You need to just explore it. So cryptography, quantum computers there that can potentially break many of the cryptographic protocols. So all the cryptographic applications that are there, banking is there, health sector is there, that are using these cryptographic protocols. They have to be reformed. They have to be again design new algorithms which are there, or you can say what we can say quantum post cryptography algorithms. Then optimization problems. Optimization problems are very common real-time problems. Traveling salesman problems are there which are using logistics in the healthcare sector are there. Then optimization of resources, that is another area where optimization is done. Again, then machine learning, as I discussed. Then there is an area of material science where quantum computing can play a major role. So overall, quantum computing has a potential to transform many fields and enable new discoveries that were previously impossible. So it has opened new avenues basically. It's not like that it's just a new paradigm, but it has certain abilities that can solve those problems which were nearly impossible or very difficult to compute over the classical computing. Okay. Now talking about the difference between the classical and the quantum computer. So these are some of the, I have tried to get some of the points as compare both the systems here. So if you can see, I'll just go one by one. Classical computers are based on transistors and can either represent 0 or 1s, right? And on the other hand, we are having qubits which can be 0, 1 simultaneously also. Then it uses transistors to create these logical switches. Quantum computers, on the other hand, that use trapped ions, superconducting loops, quantum dots, diamond vacancies to create qubits. Okay. So again, how the qubits are basically created, how the qubits are basically used as compared to the classical computers. Then multiple transistors make up the basic logic gates, multiple qubits make up the logical qubits are there. Now, next one is important. Compute power scales one-to-one relationship with the number of transistors and clock speed in classical computers. For example, if you want to increase the computing speed, we add one transistor, so the speed up will be increased one time only. But on the other hand, if we add one qubit to the system, the speed up will increase exponentially. Right? If I am talking about 2 qubits, how many states it can represent? 4. But if I am talking about 3 qubits, how many states it can represent? 8. Similarly, 4 qubits, 16. So you see the exponential rise in the number of states that can be possible. Classical computers has low error rates, but quantum computers has high error rate. Now this is a limitation. This is one of the main challenge, that error rate is more in quantum computer. The reason being, these are very, still the stabilization of the qubits is being done. It is not, entirely possible. Some quantum computers are basically, executed at less than 200 Fahrenheit, temperature. They have to stabilize. Some, if we talk about the quantum computers that are based upon the light, then again minor energy will, disrupt the state. So it's very difficult to stabilize the qubits. Now, the basics of quantum mechanics, as we discussed earlier, the two things are there: superposition and entanglement. As already stated, what is a superposition? A quantum bit can exist in multiple states at the same time, is known as superposition state. So the state at which both the bits are existing together. This allows quantum computers to perform many calculations simultaneously and speed up certain algorithms. So in order to speedify, in order to enhance the speed of an algorithm and reduce the delay, we go for superposition state. Then the entanglement, that means their states are linked even when they are separated by large distance. So that means the distance does not play any role in that. The states of the particles are independent upon the distance. As I just gave the examples earlier, if I have two particles at the long distance apart, so overall system, if it is stable, so if we know the rotation of one state, we get the rotation of another state automatically, right? Okay, now we are talking about quantum computing, qubits. We are talking about, so what are the fundamental components of a quantum computer architecture? We say okay, qubits are there, but how qubits are used basically? What are the other components that are involved in designing a quantum computer? So let's talk about the fundamental concepts starting from qubits. Now, a bit of a data is represented by a single atom, that is one of the two states denoted by 0 or 1. A single bit of this form is known as a qubit. Now let's face, this is an atom basically. At the center we know we have a nucleus which are surrounded by the ring of electrons. So let's suppose we are having an electron here. So let's suppose this inner ring that denotes state 0. So if electron is there, if I put a light on there with the frequency of lambda and time interval t, what will happen? This electron will jump to the excited state. So let's suppose this excited state is state 1, right? So this is, so far we are having state 0, state 1. Two states are there right now. We are not talking about the superposition right now. This is 0 and 1. But what happens if I throw a light pulse with the frequency of lambda by 2? If I halve the frequency, what will happen? The electron will be in unstable state. It will be either in the ground or in the excited state. So how it looks like, if you are able to see this diagram here, if I put the light pulse with the frequency of lambda, for the time interval 2, t by 2, the interval is half. So the electron will be either in ground state or as well as in the excited state. So it is the superposition state. Okay, and that qubit is basically a superposition, is in both of states 1 as well as 0 at the same time. And this is the mathematical representation, how we are going to represent the states altogether. We are having z, then x, y, where x denotes the probability of state 0, y denotes the probability of state 1. We are having one normalization condition, x square plus y square should be equals to 1. That condition has to be satisfied. This is known as the normalization condition. Clear? So this equation has to be satisfied. So there are a number of probabilities that you can do. For example, 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. If you square it and add it, you will get 1 here. That is normalization condition. Clear? I hope you are familiar with this. Have you gone through this earlier also?
Yes.
The relation, right? Okay, now the types of qubits. Now we are having different types of qubits. If you see here, we are having photonics, trapped ions, neutral atoms, superconducting loops, then silicon quantum dots, topological qubits, and diamond vacancies. Now each of the qubits have specific different specification, different pros and cons. Accordingly, they are being used by different companies that I mentioned at the bottom. So comparative analysis is being done, and again these are different categories of qubit types. Okay, entanglement, as we discussed, is a phenomena in quantum mechanics where two or more particles become linked in a way that their states are correlated even when they are separated by the large distance. The same thing that we discussed earlier. That means the states of one of the particles is dependent upon the state of other particle. Okay, so dependency is there regardless of the distance between the two. I hope entanglement is clear to everyone. Today we go in detail the theory. It is clear to everyone. That means if you have the information of one state, automatically the other state you will get the information. So concludingly, we are having. So you see, we are having quantum computing. Superposition is there, entanglement is there, with the two states are linked. Now the third phenomena is also there. That is interference. It is nothing but the overlapping, or you can say intermingling of two different states. So what happens in this is just like wave properties are there. If they are synchronous, they will be there will be constructive interference. Otherwise, there will be destructive interference. Just like how waves are overlapped. Single wave system, multi-wave systems are there. Just like in computer networking, we study. If one of the signal is going, zeros, one is going 1, when you overlap them, automatically the resultant will be neutral. Okay, so that is known as interference, and it can be constructive, it can be destructive. Okay, now
can we move to the last one? Like that in that superposition means that animation which is going on. Means there is one electron, for example, and it is either to be in the ground. But in the animation, what they are trying to show that it copies to itself. That's why it can stay in 0 and 1 simultaneously.
It doesn't copy itself. It basically it can be either state. It depends upon the probability. The probability is very important. The equation that we discussed here.
Means it is with probability half.
Yes. Because if you try to observe the state, it will, leave only one state. It will give you one state. But with the probability, we assume that it is in both the states simultaneously. Okay, so that's why the normalization condition is also there. Okay, talking about the quantum gates. So these are similar to classical gates. Classical gates means the logical gates that we discussed, OR, AND, NOT, XOR. These gates are there. Similarly, we are having quantum gates. So quantum gates are basically similar to the classical gate, but they do not degenerate output. That is, their output input state can be derived from the output state uniquely. They must be reversible. This means that deterministic computation can be performed on a quantum computer only if it is reversible. Simplest gate involved in one qubit is known as Hadamard gate. Then we are having control NOT gate. Now what are these gates basically? Just like our logical gates are there, which are used to manipulate the bits. We can perform same manipulation over qubits. So for qubits, we are having different categories of quantum gates. We are starting from the I gate, X gate, Y, Z, S, then again followed with the T gate, H gate, C naught, C gate. So these are the different gates, depending on what type of output we are looking for, how the output will be generated. So you can see at the right, we are having input as well as output, how the output will be formed. So these are the different gates which are basically used to work upon the qubits, just like the logical gates are there, how the operations will be performed, and accordingly these are used for the qubits. Now once we talk about the logical gates, then next comes the logical circuit. Similarly in quantum we are having quantum circuits, okay, that are made up of quantum gates. So these are the basic building blocks. They are composed of quantum gates which are analogous to the classical logical gates but operate on qubit instead of bits. So quantum circuits are constructed by connecting quantum gates in specific order. Now when we when we do the hands-on session, we will try to visualize how these gates are there, basically manipulated, how these are able to use or transform the bits from one position to the one state to the another state. So one of the key advantage of quantum circuit is their ability to exploit quantum superposition and entanglement to perform calculations parallel. Okay. So basically quantum circuits are used to get the output. It depends upon which type of application you are using. You have to design the circuit accordingly. So that's where the entire research is all focused, to design a quantum circuit. Okay. So designing a quantum circuit is very important. That's the main objective of our research in quantum optimization. For example, the project that we are having at NIT is about vehicular optimization. Now, vehicular optimization is a very common problem with us. For example, if I have to find the route from here to nearest hospital, okay, we are having a lot of variables in between. The path, the traffic, the time, everything is there. So how to use quantum optimization to find the shortest route? Okay, that's the project that we are having here. So what our students are doing, they are trying to design a circuit that is able to involve all these variables and find us the shortest path. Okay, so for the classical computers, we are having certain algorithms, but where the quantum will play a role, the time. The quantum computers will be able to find the path in less time as compared to the classical computers. And especially in terms of healthcare sector, time is very important, right? Even healthcare sector is there, or any let's suppose fire department is there. For any emergency services, optimization in real time is very important, considering different variables. So that's where the quantum computing will be there. However, the quantum circuits are also susceptible to errors caused by environmental noise and other factors. Now these are very important, that will lead to errors in quantum computers, because as I said earlier, it is very difficult to sustain or maintain the qubits. So even environmental noise, even sometimes what happens when you are running a quantum algorithm in our local simulator on a local machine, even the this charging of the laptop will be able to disrupt the output. So very little noise is required. So some errors we are expecting, okay, but if we are expecting 95% of accuracy, we are getting it, so that is fine with us. Okay, because noise should be very minimal in case of quantum computers, environmental noise. Okay. Then quantum algorithms. So this is one of the area where my research scholar is already working upon, to design quantum algorithms that will be deployed over quantum machines. Okay, because quantum machines, as we know, companies are able to develop it. Google is claiming that it has developed quantum computers that can support more than 2,000 or 5,000 qubits. D-Wave company is there that is supporting more than 5,000 bits. But how, or what are the algorithms? Whether our classical algorithms will be able to deploy our quantum machines? Because our classical algorithms are only made for our classical machines, that are not made for the quantum machines. So we have to transform those algorithms altogether. How we can run it on a quantum computer? Let's suppose a simple quick sort is there. We cannot run a simple quick sort on a quantum algorithm or quantum machine. Okay, so we have to design new algorithms. So that's why where one of the scholars is working upon. So quantum algorithms harness the power of quantum computing and offer groundbreaking solutions to complex problems that classical computers find challenging to handle. Algorithms provide clear advantage scenarios where classical method face computational bottlenecks. The ability to explore numerous possibilities simultaneously allows quantum computers to outperform classical counterparts in specific problem domains. So again, the same thing is mentioned here, that once we are able to explore quantum algorithms, they will be able to surpass the classical algorithms. And also there is one more paradigm that I want to explore here, is quantum inspired paradigm. Now this term quantum inspired is different from quantum algorithm. Quantum inspired means that we are designing an algorithm that is inspired from quantum computing, but we are able to execute that algorithm over our classical computing system. I can deploy a quantum inspired algorithm on our local machine without any quantum simulator. I don't require a quantum simulator to run a quantum inspired algorithm. I can run it. Okay. So quantum inspired is another, one of the research direction that is there. Okay. So the scale of the problem depends upon the configuration of the computer, the platforms for various quantum services, including simulators, quantum hardware devices, GPUs, high configuration, classical computers. So these are different, simulators that are there. We are having Google Search, QSkit is by IBM, Amazon Basket is there. Now this is the, Amazon Bracket is there. So this is the simulator. We are having the credits of more than 8 lakhs with us. At the NIT, the project is basically providing us credits for this. Then Microsoft Quantum Development Kit is also there. If you want to use it, I think Circ is available. I think you get a Circ available for practice. I think Amazon also provide one. IBM provides Composer is there, na? So IBM provides one of the tool is simulator is Composer.
An open source platform.
Composer is there. I think it is an open source. Composer.
Yes.
Composer is open source. Otherwise, Amazon is there. It is very good Amazon, but it is not an open source. Basically, you get a subscription based charges are there. Rigetti is there in Amazon Bracket. Rigetti is not there.
So only mainly they retired from quantum.
D-Wave retired.
D-Wave also because Rigetti is there.
Rigetti is.
Sir, at point number 3, why it is the specific problem domain? Can't it be generalized solutions?
Sir, जब हम कोई भी algorithm design करेंगे, whenever we designing algorithm, it will be targeted to specific domain only, sir. Because we cannot design a generalized algorithm. But if we are going to want the result,
Okay, algorithm can be different for different domains.
yes,
But it will outperform only in a specific problem domain. I mean, there may be some other domains where it will not be outperforming classical computing.
I'm sorry, I'm not getting sir, the question. You are saying that the ability to explore numerous possibilities simultaneously allows quantum computers to outperform classical counterparts in specific problem domains. Yes.
It means there are certain domains in which quantum computer will not outperform the classical computer.
Sir, it depends upon again the application. The reason being, in some problems, you're right. It might be possible that the quantum computer is not able to perform better as compared to the classical, but due to the errors. Because if we are having an application which involves lot of noise, quantum computers will not work. Even though we can design an algorithm, but it will not work because the error rate will be very high. If I get a accuracy more than 90% classical, I am getting 80% accuracy in quantum algorithm. Why I will go for the quantum algorithm then? It's not like that. I'm saying that quantum algorithm will always have a better accuracy all the time as compared to the classical. But the main advantage is the time, because if we have to satisfy, we have to map time and accuracy, then we have to compromise with one of the variables. If you want the time, then you go for the quantum. If you want the accuracy, you have to check with the classical.
Right.
Okay, moving on to the quantum algorithm. So as I discussed earlier, we are having Schur's algorithm, Grover's algorithm are there, then quantum approximation, optimization algorithm. Now I'm again emphasizing on the Schur's algorithm again. That can factor large numbers exponentially faster than the classical algorithm. I gave an example at the beginning of the 256 key cryptography that the Schur's algorithm will be able to disrupt, will be able to break those protocols very easily. Then Grover algorithm, as we discussed, that can search an unsorted database of n entries that order square root n times. Okay, we are having unsorted data elements. When we compare it with our classical searching algorithms like linear search, binary search, so this one has the better running time. Overall, the quantum computers have the potential to again revolutionize many fields and enable discoveries that were previously impossible. So concluding about the quantum algorithms, so we say we are having 4 different domains. We are having quantum error correcting algorithms, quantum inspired classical algorithms, pure quantum algorithms, and hybrid quantum classical algorithms. So all the 4 domains are there, which are very open research areas. Pure quantum will work upon the quantum machines. quantum inspired classical algorithms, that will be, as I mentioned earlier, that will be we can basically run them on our local machines that are inspired from quantum computing, but that are not pure quantum. Then we are having quantum error corrections algorithms are there. Then hybrid quantum classical. That means there are certain simulators that that use the local computing power also, that also use the quantum computing power that is available in the cloud. So hybrid cloud and hybrid quantum and classical algorithms can be designed. Okay, in Amazon AWS also we are having one local simulator, one cloud simulator is there. So you can perform on our local simulator also and the cloud simulator also altogether. So these are hybrid simulators. Then error correction. Quantum error correction is a set of techniques used to protect quantum information from errors caused by environmental noise and other factors. So what are the techniques that we are using? We say that errors are there in quantum. If the errors are there, why we are still going for the, or why not we are doing something for the errors? So we are having certain error correction algorithms, or more specifically quantum error correction algorithms that are there. Quantum information is fragile and can easily be disrupted by environmental noise, which can lead to errors in quantum computation. Again, if I'm saying if the result is not accurate, then it is of no use. We require accuracy of certain levels so in order to accept the solution. If we getting the solution of 60% accuracy, we will not be accepting it. At least we are having certain threshold that the classical is, if the classical is getting 80%, at par 80% accuracy should be required, should be acquired by this quantum algorithms. Only then we will be shifting it to that. So this error correction will be is there. How we are correcting the errors. One of the key techniques used in error correction is the use of quantum codes, which are codes that encode quantum information in a way that allows errors to be detected and corrected. It is entirely different domain how the quantum errors are corrected, how these are identified, and what are the correction algorithms. So lot many research avenues are there in this area. It has to be explored. One of the research scholar at NIT, she is working on this quantum error correction and how we can use that, especially in quantum communication. How the quantum bits can be when it is basically communicated from one point to another, how the errors are connecting in that. Okay, so again very open research areas there. Quantum error correction is essential for reliability of the quantum computing. Errors can accumulate quickly in quantum computations. By protecting quantum information from errors, quantum error correction enables us to perform longer and more complex computations on quantum computers. So again the same thing for quantum error corrections again is a very important for quantum computers to sustain in our real world applications. So we need to explore different algorithms, how we can correct the, how we can identify the errors, how we can correct them. Okay. So how quantum computing working is there. So this is just a basic layout how the quantum computing working is there. So you see at the bottom layer we are having the hardware, the quantum hardware is there. At the middle layer we are having the quantum code, where we are having the compiler which is made up of transpiler and optimizer. And at the top we are having the different applications, machine learning, optimization problems, simulations are there. So how the source code will be transferred to the instruction generation of the quantum bits, and again that can be deployed depending on what type of hardware you are using, whether you are using superconducting trap ions, neutral atom ions. So this is just a 3-layered architecture how the quantum computer works basically. Okay. Now there is one more classical hardware I mentioned at the right side there, you can see there. We are having code emulator which will basically convert the quantum source code in the code which will be executed over the classical hardware. That is the hardware that is available to us. Okay.
So we have complete circuit in this.
Circuit will be here, sir, in the quantum code. We will be designing the circuit here. This circuit will be designed where the compiler, this is the compiler, where the execution will take place. All these components are there, where these shorts will be run. There are shorts in when we run the algorithm, quantum algorithm, depending on the task we are having. Okay, so that will be executed over. Once we design a quantum code is basically a form of a quantum circuit basically. Okay, so that's what we are going to execute.
Sir,
question. Is there a problem of vendor lock-in in future?
तो वेंडर लॉकिंग का आ सकता है क्योंकि अभी लिमिटेड कंपनीज हैं जो क्वांटम प्रोवाइड करती हैं, ठीक है. सो बट आई थिंक सफिशिएंट कंपनीज आ गई हैं हमारे पास. गूगल है, माइक्रोसॉफ्ट है, IBM है, जो और रिगेटी है, D-Wave है. कंपनीज आर इम्प्रूविंग. सो वेंडर लॉकिंग आई मे नॉट फाइंड एनी problem in the future because everyone is now developing quantum computers and they are claiming that they are supporting this number of qubits. So vendor locking may not be an issue, but right now it is an issue because for us also we are using AWS also. We cannot go to anyone else. But again, one important thing you have made is that how we can map a solution from one cloud platform to another cloud platform.
That cloud portability is not there.
Right now it is not there, but obviously research has to be done. Some intermediate form of solution you have to develop, which can be, we can port it on another cloud platform. Okay, for example, not the cloud platform, basically the company, for example, D-Wave is porting whatever, Rigetti is there, Amazon AWS is there. So depend upon what type of they are supporting, we have to ensure the portability, but right now it is not there. If, for example, I give you one example here. One of our students, she was working on quantum optimization problem, which was we got D-Wave quantum computers basically. But at the time we got the project, before project they were saying that Amazon supports D-Wave. But once we got the project after 15 days, they said we don't have D-Wave now. So she was stuck basically. So yeah, the problem right now it is there, but in future it might not be there. So just next is just a illustrative diagram. If you see the difference between a quantum computing and a deep learning. So at the left side we are having deep learning, a neural network. We are all familiar with what are neural network hyperparameters are there. Now this is how a circuit is made. How the circuit has to be made, how the bits will be confined. Again, if you talk about the variables in the deep learning, we are talking about the neural network, hyperparameter activation functions are there. At the right side, we are having links, how the one bit is linked to another link, qubit weight, the training data, again the variables are there, how the training is done for each of them. So this is just a illustrative, I try to map the deep learning with the quantum computing. Pani. Again, quantum computing is a very, quantum computing is again a very novel or open research area. Lot of work has to be done in this. A lot of work is being done. But if any new research scholar, any new student who wants to explore this area, it's very open field, and basically, can a lot of government agencies are there that are providing funds for this. As you already know, we are having this AWS that is basically project supported by MIT itself. So other agencies are also there that are providing it. In fact, if you might have heard about the National Quantum Mission that is started by our Honorable Prime Minister. More than 5,000 crores of fund has been allocated to different, will be allocated to 12 quantum labs across the country. That's under National Quantum Mission. Okay. So again, so it is now very, you can say government is also encouraging to develop quantum solutions. Okay. Next is about the case study. I want to discuss about this research paper that I basically worked upon. This is during my PhD. I wrote this paper. Basically, it's about the network optimization. Why I have mentioned this paper here as a case study because IoT, we all know that it is a very used in real world application. Now everyone smart application, smart cities there. So how quantum computing can be used for IoT network optimization? Because quantum computing is used for optimization at a primary level. Okay. So what is IoT network optimization? I just want to give you one example here. For example, I am standing here. I have, let's suppose, 5 sensors across me in my ambience, and one sensor is located far away, one sensor is located closer to me. So If I ask you which sensor will give me the correct observation, the one that is closer to me. For example, let's suppose my temperature is there using laser or anything, whatever the sensor is there. So the sensor which is located closer to me will give me more accurate information as compared to the sensor that is far away from me. Okay. So what I have tried to done in this research paper, I have tried to optimize the network around the object. Okay, that means around the object as well as around the sensor as well as. For example, if I talk about the sensor, what is the range of that sensor? What is the network around the sensor that it can sense? It should be allowed to sense. If I have this data and that sensor data which is located far away, if I accumulate both the data, let's suppose I take the average of both the sensors, my average will give me less accurate result as compared to the sensor which is closer to me. If it give me, let's suppose, 90% accurate result, if I take that data itself, it will give me 80% result. So my accuracy decreased. So what this research paper did, it basically we narrowed it down this sensor space around any object. As we know about the Gartner hype cycle, quantum machine learning is there. This is the hype cycle for 2021. As you can see, quantum machine learning is at the rising end of the Gartner, and it will be there for more than 10 years. Okay, and where we are right now, we are basically at this point where the quantum machine learning will be impacting AIs and futuristic use cases will be developed. Okay. There is one specific field that I want to touch here is about the genetic programming. Everyone who has done work on genetic programming, this is basically a branch of soft computing. Genetic programming. Anyone? I'll just brief. क्या होता है इसमें?
Is it genetic algorithm or genetic program something different from genetic algorithm?
No, it is same. Inspired from this genetic programming. You know what is individual chromosomes are there? Yes. No.
I did work on that.
Okay. So sir has so basically we are having one individual there. Then we are having population. Okay, I'll start with the basic. Let's suppose what happens in this is there is a concept of survival of the fittest. Okay, there is one theory at Darwin's theory, if I'm not wrong. Survival of the fittest. So what happens in this is these individuals, basically what are these? These are different qubits. Okay, so multiplication of qubits will become your population. Okay, so I have worked on these population part, and basically with the different iterations, whatever qubit will be more stable, that will be sustaining, otherwise it will be removed. Okay, so the something concept of that is more giving me more accurate result, that I am continuing with for the solution, other one will be removed. Okay, so this is basically used for optimization. Okay, genetic algorithms are there. So let me come to this sensor part. I'm just going to quickly overview of this proposed algorithm that I have designed basically. So we are having two things, sensing ability and sensor in vicinity. The two things that I have quantified. So what was the problem basically? So the three-dimensional coordinate space is comprised of multiple sensor and object. Based upon the quantifiable measure of the sensor specific parameters, it is essential to minimize the data acquisition space for a particular object. So that means the sensing space around the object, that is optimized. That is known as the optimal sensor space. And for the sensor, we are having different parameters. For example, if I talk about the range, accuracy, span, precision, sensitivity, linearity, all these parameters were mapped over qubits. So accordingly, the sensor individual is there, sensor population was made using mathematics and different iterations. We were able to get the optimized result. So if I talk about the algorithm, though, this is the algorithm. One, we are having two types of procedures. We are having local search procedure, and the second one we are having global search procedure. So this is the core algorithm that was designed, for this research paper. I'm not going in detail about this specific of the algorithms. If anyone wants interested, it is available online. Okay, so it can understand it, and it was very it was published in 2020. If I take this is 2023 ending, so it is basically 3 years old paper. but still it is very, I find it one of my good research work, and it's published in more than 10 impact factor. Anyway, next is okay, with respect to the research paper itself, it's for the performance indicator. So what are the indicators that in which I measured the performance of our algorithm? So one was data accuracy, how much accurate my data is. Then second one is temporal efficiency, how much quickly I am getting the data. Then the final one is data cost, how much cost I am incurring. Okay. Next is about the applications. Very generic applications are there. I'm sure you are all aware of these applications. Talking about the artificial intelligence, drug design, cybersecurity, financial modeling, and we are having different problem types, optimization and machine learning problems. Traveling is there, retailing, telecom, aerospace. All these problems are still open. A lot of work has to be done in these problems. So that's why I said, if anyone interested in working upon this quantum algorithms or quantum applications, he or she can choose any of this problem and design certain algorithms for the quantum machines. It's very right time to work on the quantum computer. Why? Because it is still developing, and if it is still developing means, if you are working on a research paper, it is a very good chance to get published in a reputed SCA journal, if you are working on this new area, because once it has evolved, then it is very difficult to publish. Okay, so it's very starting phase. So we can work on it. So quantum simulators, as I discussed earlier. So these are Microsoft, Atoms, IBM is there, D-Wave. We are having with us at NIT, we are having Rigetti is there. Then D-Wave, Eon Q. Yeah, this Eon Q is available with us. Rigetti is there. दो ही हैं और अभी दो कौन सा? अच्छा Zen2 इसका भी है हमारे पास. अच्छा टैग. Okay. Earlier we were available with D-Wave also and Zen2 also, but these are not available now. Again. That's why the search vendor locking concept comes to mind, that we are dependent upon the AWS only. Okay, available quantum computers. So we are having IBM's, Google's, D-Wave, and we are having number of qubits that they support. Now, as I said earlier, D-Wave was there, which claimed more than 5,000 qubits, which are used for the optimization purpose. Then Honeywell, Rigetti is there, Zen2, Microsoft. So all these quantum computers are available. Okay, what are the challenges and limitations for quantum computing? Scalability. Building a large-scale quantum computer is a major challenge, as number of qubits needed to perform useful computation increases exponentially with the complexity of the problems. So the large number of qubits, it is very difficult to stabilize, ensure how we are going to use these qubits all together. Then environmental noise, as I mentioned earlier, environmental noise is the biggest challenge. A limited coherence time, that means qubits have limited coherence time, which is amount of time that they can maintain quantum superposition and entanglement. Now, quantum superposition means existence of simultaneously multiple states simultaneously, but for how much time that these states can be coexistent. So that is the coherence time. So these qubits have limited coherence time. So we have to this is again a limitation. Again, limited gate fidelity is there, limited access. Again, quantum computers are currently only available to limited number of organizations. But I'm sure with the time, lot many organizations will be able to develop it so that we are free to access quantum hardware. Talking about the future of quantum computing, hardware development companies such as IBM, Google, and Rigetti are developing new quantum hardware that can perform more complex computations. Software development, researchers are developing new algorithms. Quantum networking is there, quantum machine learning, quantum supremacy. All these are open areas where a lot of research is being done, a lot of development is being done around the world, and I'm sure it is a good area for research. For the research directions, for architectural perspective, you can work upon the optimization. You can use quantum machine learning to solve linear algebraic problems. PC analysis, principal component analysis, there, SVM, quantum load scheduling, deep quantum learning, quantum neural networks. You see, all these are basically nothing but a quantum version of classical techniques. You know, we are having linear algebraic problems, we are having PCA analysis, we are having sport vector machines for AI. So we are just basically using quantum form of them. We are developing quantum form. For application perspective, cybersecurity. Cybersecurity will be the main area. One of the, not the main, but the premier area where quantum computing will play definitely a major role. Financial modeling, logistics, weather forecasting, traffic, energy efficiency, drug design, manufacturing, industrial design. So all these are open areas. Again, these are, you know, at the best to my knowledge, but more areas can be there. Yes, it is again a very researchful topics that you can explore, and obviously you can get published and you can design patents, you can write copyrights for that. You know, it can be done. We are having one tool there known as Sidespace with us at NIT. So what this image is depicting is that, you know, how the quantum has evolved over time, and what are the areas that has been researched. You know, how we have done is we get the data from the scopus from the last if you say 12 to 14 years, and we see how what areas are explored, how much research has been published. You see, quantum machine learning, quantum algorithm, quantum simulation, post-quantum cryptography. So as per the years, how the research work has been done globally. All this data has been acquired from the Scopus database. Okay, so we use this Sidespace tool there. Then again, what are the prominent research areas? We are in quantum algorithms, quantum simulation. Again, the same data is being used. We have drawn this network graphs from Sidespace itself. In the Sidespace, similarly for the quantum communication and quantum error correction, then quantum machine learning and post-quantum cryptography. So all these are areas where research can be done. Okay, what are the countries that are collaborating, that are contributing to the quantum research? You know, it is very much familiar with the size of the circle denotes how much work is being done. I think it's obvious. You see the China is there, USA, Canada, England, Australia is there. There is India is there. So research is being done. Again, the data source is Scopus. So they have developed this graph. So which country is producing how much research, how much research they are doing as per the publications in the quantum domain. As per the global status, financial global status, so country-wise distribution is mentioned here. You see, US has basically a National Quantum Initiative, $1.2 billion. Then for India it is $1 billion. Then European Quantum Flagship Program is there, 1.1 billion. France is there. So, you know, you can see throughout the globe, most of the, you know, big countries have basically, you know, supporting or putting a lot of funds to the development of quantum computing. You see, the China is there, more than nearly $10 billion they have spent in developing quantum computers. So you can see the global estimate effort for quantum computing development is $22.5 billion. So this is a sort of a, you know, illustrative view how the funds are basically utilized across the world for development of the quantum computers. About the institute, which institutes are there that are having quantum, that are, you know, working upon? MIT is there, Harvard, IIT Madras, Princeton, CMU, IIC Bangalore is there, PIFL is there, Zurich is there. So all these are having supporting this quantum computing. They have, you know, their own research lab that are only dedicated to quantum computers. And as for the Indian perspective, we are having government agencies, Ministry of External Affairs, CDOT, telecom industries, then startups. These are all startups that are focused on the quantum computing. In academia, different institutions that have either they have labs in their institutes or they are having quantum course in their curriculum. Okay, so these are the different institutes that are there. Service providers for the quantum technology. this was the project I was talking about. We are having, so this is just a snapshot. So at the moment we are having around $3,000 of credits for the Amazon bracket, and the remaining 7,000 will be credited shortly. So this is for the duration of 12 months. Specifically started for 31st May. So I'm the co-PI in this project, and so this is supported by Ministry of Information and Electronic Technology, the QCAR project. So so this was from my side, and the next hand-on session will be discussed with by my research scholar. And any doubt for the presentation that I mentioned, you are free to ask anyone. Otherwise, hands-on session will be discussed by
Any example of quantum inspired algorithm?
quantum inspired. I have mentioned my research work that is only quantum inspired. The genetic algorithm that is inspired by quantum computing itself. So that's why in the title also it is quantum inspired. If I show the title itself. Quantum computing inspired network optimization. So that is a quantum inspired genetic algorithm basically. So that is inspired from quantum, because at that time I was not having access to quantum hardware. So I used the quantum computing, mapped it over to the local genetic algorithm and designed the algorithm for this. Any other?
So how could we inculcate this particular thing to students? How could we pass?
So that's what I was discussing with sir also, that whether we have this in the curriculum itself or not. We at NIT are also designing a course curriculum paper for this for the students. For the timing it will be an elective, but it will be there. We are designing a syllabus for that. We are also referring to different IITs who are already teaching this. So it's better to start with the theoretical concepts of quantum computing, because it's basically inspired from physics. Okay, so physics is the backbone, because our computing students may not have physics at the background. So we have to start from the fundamentals, and we can have a lab attached to them. And if the open source, for example, IBM Composer is there, we can at least give them initiation, how to deploy a qubits, how to design a circuit, all things we can do. And I think some codes, is it GitHub available? Some codes, quantum algorithm, AWS has shared us. We have certain GitHub repositories which provides quantum algorithms. My students are having us, because in our project now we are having direct meeting with Amazon every monthly. So every month they have a meeting with our students. In fact, this project is being spread across the country. We are about, I think, 20 to 30 institutions that have this project. So we have a meeting every month. So they provide us all the links, whatever problems our students are facing, they provide a solution. So they have the repository with them also. It can be used by the students all together. So it will be available. I think we can make it public. It's not a big deal to hide it there. So yeah, students need to be made aware of this, and I'm sure within the coming time, let's go 3 to 4 years, it will be there, because we are also modifying our syllabus as per NEP. So we are including this subject also. In fact, the Amazon AW has offered us that they will provide us industrial experts to teach this certain topics of AWS at our institute. So it's basically last week itself this same meeting was there about how to improve this course. So yeah, it is necessary for students to understand this. And is any other?
So my background is physics only, and
So you will be more
no, I can understand the things, but implementation, as per implementation, I means very lost at from where can I start this, and which thing I can pursue, right?
Look, implementation, open source IBM is there.
Right.
IBM Composer is there, but it is, I didn't find it very much useful, because it is open source and limitations will be there.
Right.
The AWS, it is very AWS bracket we have. It is very much had all the tools with us, local simulator, cloud simulator. It is available, but again it is paid. It is subscription based, and but I'm sure with the time, some companies might provide better solution, open source, so that will help the developers to develop code and design solution for them. Starting, you can explore AWS bracket. I'll suggest that only. I think most of the theoretical concepts will be there, that what is there in the bracket. I mean, bracket is a repository where different tools are there. So you'll get to know about the tools, how they work, but you might not have access to the tool, but the information you will get it. Okay. So once you are able to get the access, and whenever you will get the access to it, so you can use it. So start with the Amazon only. Amazon AWS bracket is there, so start with that.
And what's procedure for that? What is procedure for that?
And I'll explain.
Okay.
He's going to explain about Amazon AWS. उसका subscription वाला करेगा, dummy करेगा?
सर मैं अपना ओपन करके
Dummy वाला?
हाँ
Because we are having subscription, but the problem with the subscription is that if we use it, it will incur cost. हमारे पास $3,000 की है cost, लेकिन the thing is, it is very limited. 3,000 is not a big cost, and if it is left open, this cost will run out in the entire night only. ठीक है, तो हमें वो जो सब्सक्रिप्शन वाला वर्जन है वो बहुत हम ध्यान से यूज करते हैं, ताकि once it is finalized, the algorithm is finalized, only then we will deploy it over there. Otherwise, what our students have done, they have made a dummy card. You require only any debit card for that, for login. उसमें कोई charges तो नहीं है, कोई charges नहीं है. So we have made a dummy login, so they can explore how the bracket looks like. So you can start with that. So that is there. He will show you how this working will be done.
Excuse me, sir, subscription is like time bound in terms of number of years, in number of hours of from starting date, or in terms of uses?
Cost.
Okay.
If it is in terms of how much you use, it will incur a cost.
In terms of uses, it is in terms of uses.
You are basically you will be paid charges. Just like in cloud computing, pay as you use model.
Right.
So if I'm using it, I will be charged. I have a budget of $3,000 right now.
Right.
So if I use it, budget will decrease.
Right.
So that's why I'm not using the subscription at the moment, because we have reserved it for the students specifically for searching. But dummy, he will show it. We have created one dummy account also for students for practicing. It doesn't give access to your quantum hardware, but it will give you the information about the libraries that are there, the other components that are there in the Amazon bracket. I'm sure you will be able to know this once he opens up the hands-on session.
Right.
Any other? Because Amazon AWS is very helpful tool. You get all the resources online. If there is some issue there, you can even contact their customer care. Even you can get the resources on their GitHub itself. You get the resources. They have basically that's why they have tied up with the MIT. Okay, MIT is a government Ministry of Information and Electronic Technology. They have selected Amazon to provide the quantum information resources. Okay, so obviously they have chosen Amazon for a reason only. And Amazon, we all know, it is very famous and very resourceful techniques, and a lot of research is done by our AWS itself. Any other doubt? Look, simulation is a challenge, I agree, because we are talking about the quantum computers. If you don't have the resources, what's the purpose of understanding? We need to have resources for that. I'm sure once this our quantum machine, different labs will be set up across the country. Let's suppose if nearby, I think it's IIT Ropar is there. If the lab will be set up there, I'm not sure. If it is there, so we can have the approachability. I think we can use the resources from the IITs also. Okay, and we are also trying to develop a lab in NIT, but it's very challenging right now. So yeah, resources will be there. We have to migrate to some other institution to get it. That's the only solution for the time.
So when we talk about the development of this lab, what things will be there in that lab?
So the things, sir, there are two solutions. One is the cloud resources will be available in the lab. That means, for example, IIT is given us specific credits by the government. They will be given certain funds by the government to purchase the quantum hardware, which is available from the cloud itself. So certain computing machines will be there that will having access to the quantum hardware. So that is my number one solution. The second solution is to deploy a quantum computer, which is not possible, sir, at our local
When
labs.
quantum computers are not feasible, I mean, we don't see in near future we can have the quantum computer in our institution.
We cannot have.
And when we can have the only through the cloud, then there's no purpose of having the lab. It can be searched from anywhere.
Sir,
Then why we will call that specific area as
so the
quantum
reason
lab?
being the subscription, because if specific lab is having the cloud resources, paid cloud resources with them, either we purchase it ourselves, or the lab is having the resources, we can tie up with the IITs to access that lab rather than purchasing on our own.
No, that means it is only the access
Resource
point.
share,
It
yes,
is only
yes,
access
yes.
point.
Only.
Okay, it will be resources are on
It
the
is through the
cloud.
cloud only. It's nothing like that. We can use it if we pay amount here itself. We can get the resources here.
And if we can have a simulator in lab, then can we call that lab as a quantum lab?
Yes, obviously, because the simulators are available within the lab. The machines are there that are having access to the quantum hardware. We cannot say the quantum computer is there, but quantum accessible hardware is there. At the starting point, initial phase, we have to start with that. I cannot say we develop a quantum computer in the lab in my NIT right within next few months. I mean, that is not possible for me because it is very difficult to stabilize the quantum computer. So even the big companies are there, Google are there. These are very big companies. They have spent a lot of funds to develop a quantum computer. So we are able to access those hardware through cloud only. So if we pay the charges, then they will be charging us for accessing it. Just like we are using Amazon AWS.
Okay, sir. Is there any real problem which has been solved by the quantum computers till now?
So real problems.
I mean some problem which was not solvable earlier by and with the available quantum computers we are able to solve that problem now. For first time we are able to solve with the quantum computer. Earlier that problem was not solved at all.
Sir, the problems were solved, but I think the constraint was time. Just I mentioned one algorithm there, Peter Shor's algorithm, Grover's algorithm, that basically identified sorting unsorted arrays of characters is there that is able to find or search an element with the order of square root n times, which was previously solved by the classical computer in order of n times. So, in terms of time, the quantum algorithm was better. It was solved by the.
So that problem was solved only.
Problem was solved
time
yes.
has been reduced.
Yes, time. So that's why that was the key aspect of this quantum computing is that the time it takes to solve it is comparatively less as compared to the classical one. Because in NP problems, when we say NP problems are that the problems are solved in non-polynomial time by the classical computers. That means we don't know when it will be solved. That's why it is called NP problem, non-polynomial time. But if we talk about the quantum computer, it can solve it in polynomial time. So the time aspect is there. If we want the result in real time, we can get it. If we don't have the time constraint, obviously the problem will be solved by the classical also, but the time will be there. And another aspect of your question that some problems which are not solvable earlier, which can be solved now, because
which has been solved. I mean, if are such quantum computers
I'm
available,
coming to
or
that.
they will be in future only.
Because why I'm emphasizing on NP problems, that we are not sure that those problems will not be solved by the classical computers. That's the dilemma of this NPP problems are there, sir. NP says that problems will not be solved in polynomial time. But we are not sure that these are impossible, they are not solved. Maybe in 10 years or 15 years time, some scientists will develop an algorithm that is solvable on classical computers. But for quantum computers, that will be solved in polynomial time. So that's the enigma, the why P, we have the relation P is less than equal to subset or equal to of NP. It is not equal to NP, not less than NP. We have having one data structure equation P and NP, P NP problems. P is the problems that are solvable in polynomial time, NP is the problem which are not solvable in polynomial time. That means that are solvable non-polynomial time. But when those problems will be solved, we are not sure. And we cannot say that these are impossible problems. Because maybe in future time, somebody solve it. We are not sure that those problems are not solvable. If you give me a problem, if I run it I say it is not solvable by me, but I cannot claim it that this is not solvable. Maybe someone else will solve it. So that's the enigma is there, how to P and NP problem, and same aspect comes to the quantum computing itself. If you give me a problem, I say it is a solvable by classical computer, but when it will be solved, I don't know. In classical computers, but in quantum computer, it will be solvable in less time or in polynomial time. So that's the mapping is there. Okay. I think we diverted to the data structures for the moment. Anyone else? I hope you're everyone familiar with the PNP problem that we discussed.
Yes.
Sabko pata hai? Any else? Anyone?
So we have heard many times that in quantum computing, measurement is a major problem in which the superposition is lost and we get. The question in my mind is that then what is, are we running after something logical or something very hypothetical in that way?
Look, it is not a hypothetical, otherwise no company have worked on it. They are searching more than more than $20 billion on this for not for hypothetical.
So has that been realized ever? Like in D-Wave, they were saying that it is not actual quantum computing. They have used something else to act like that. This was some news that came after that D-Wave announced.
Look, in the starting I mentioned one historical graph. The concept was developed way back in 1900. Hypothesis was there about the quantum mechanics. So with the passing of the time, the technology has existed that is able to assess the state. Okay, that's why quantum computers have existed. Otherwise, quantum computers would have not have existed. It would be on the only theoretical concept would have been there. But the technology, we are able to access the state. That's why right now it's a lot of boom is there in quantum computing world. That they are claiming, or I'm not saying claiming, but they have patented or they have developed certain systems which are basically inspired by quantum computing itself. They are able to access the superposition state, even though unstable, but they are able to get it. Okay, so instability is there, error the main aspect is this. So issue is there, but again research start with the issues, we solve the problems with the time, and eventually we will see in future, in coming 5 to 10 years, the quantum computing is easily accessible. Right now, which is not, but with the government of India also taking initiative in terms of national quantum mission, labs will be set up which can be accessed by the students. So I'm sure a lot of work will be done. Okay, and security aspect, as I said, post quantum cryptography is again a very important area. One of the students is working upon the same research field, so that can be worked upon. Quantum communication is there, how to transfer the quantum data, and the quantum algorithms. He's working on the quantum algorithms, and other areas, applications. If you want to go for application specific areas, that can be done. So it's not a hypothetical; it's a basically logical aspect, and basically we are removing this notion of hypothetical and bringing out the logical. Okay, it's not a hypothetical anymore. So yeah, it is not a wastage of money basically. Okay, yeah. Anyone else, or should we start with the hands-on? Okay. So
Classroom may have a tea break, short tea break, after that we will shift to the lab.
Okay.
Hands-on session. This is the outlines of AWS account. Okay, AWS is a platform, AWS Bracket, where we deploy quantum program. There is a Jupyter notebook there in AWS Bracket. On the Jupyter notebook, you have to write a code in Python. According to Python, the code is running, and then there is also a local simulator and other cloud simulators. So this is a AWS Bracket. I log in. I'm logging there, but if you want to log in, There is a page of AWS bracket and sign in. There is a two type of user there, a root user or app user. Root user is a major user. If you get credential or you have an account on AWS bracket, then you also create your own other root app user, root source users. And
This may act as an admin user.
yeah, root is the head, and there is another sub parts of roots. Here you have to create. This is the
सर रूट यूजर से करना सीखा
actually मैं जितने बजे कर सकता फर्स्ट ऑफ ऑल क्रिएट करोगे ना तो तुम रूट यूजर का एक्सेस मिलेगा
जी
उसके बाद okay this is all we need to fill it like here give a verification code on your email account. This is a verification. You can create a new account here. पहले से अकाउंट है तो उसमें नहीं होगा मैं नया आपको आईडी डाल के दे देता हूँ
Talking to your ID.
Okay, sir.
It's a simple sign up page. जैसे normally sign up करते हैं. ठीक है, you get a verification code on your account. उसको click करो, you will log in. Normal sign up page है, किसी भी account में log in करेंगे. उसमें already email ID को use करके account बनाया हुआ है. That's why it is not showing up.
You can leave it. You can log
Just
into
sign
your own
log into
account.
your account.
Okay, sir. इसमें ये free subscription कुछ time के लिए होती है जैसे
Actually sir, there is a debit card enroll in that account, debit or credit card. If you there is some 100 to 150 slots are available there. If you not use that much slots, then there is no money. And if you access maybe आप ऊपर चले जाते हो उससे तो आपको पोस्ट पड़ेगी. और इसमें ये होता है मैं भी दिखाऊंगा आपको नोटपैड बनता है हमारा तो अगर वो this is the account I have and there is the services. All the cloud-based services which provided by AWS are here, and this is a quantum technology, and here we are. We are here with the dashboard. On the dashboard there is a announcement and community reporting are there. Announcement that means which quantum computer is retired or which is new purchases by AWS, and this is devices. Actually there is a there is 3 simulator which is available now. First 3 SV1, TN1 and TM1. This is the 3 local simulator. Okay, other is a computer, other is a quantum computer. IonQ, Oxford Quantum Circuit, Cura, Rigetti, there are the quantum computers which we use for the purposes, different purposes. There are the descriptions are there like 79 qubit universal gate model superconductor qubits, 256 qubit along analog neutral atom based PU, and IonQ. Different IonQ are available there. there is one more option. If this is not available, you have to change the location or access area. There is a US. Now I am in Virginia. If you change and California and another, you have to change. Maybe there is available that particular computers. And this is a notebook. This is my notebook I create earlier. But if I create new one, this is a create new one, and here we give the name. There is a mode, light and dark. Is a visualization available. That's all. Like. Review and launch. There is not space for that. This is the description, general setting, notebook configuration. There is no GitHub repository cloned. This is for your repository. Earlier you used the GitHub all. GitHub, there is a repository, and you all have to copy that repository and the paste here in the notebook. And this is the overview, and we launch this. It takes some minutes, but if we check it, we have already in Surface notebook. This is the interface of notebook. Here we have our folders, bracket algorithms are there. Different bracket algorithms you want to know, you want to read it if you want to. What is the Monte Carlo, and all the descriptions are here for you, and the code also here available. But firstly you have to understand what is the Monte Carlo technique and all the stuff up there. And the analysis are also there. There is a button for repository. There is a button that is the repository. If you want to include any repository from GitHub, this is the for it. Clone a repository, initialize them. This is a feature. If anyone familiar with the repository, it will be first. If you want to use repository here, you have to firstly create the repository in GitHub. Maybe it may be available for your convenience, but maybe not available. You have to आपको करनी पड़ेगी वहाँ पे न्यू में भी बनानी पड़ सकते हैं, मे बी आपका मिल भी जाए, डिपेंड करता है जो सा आप काम करते हो. इट्स नॉट मच क्लियर भी आपको मिल ही जाएगा. Here we have to launch, start a bracket, and this is the first code of quantum. All you know about the well state. वेल स्टेट का पता ना. हाँ, तो वेल स्टेट का फर्स्ट कोड है यहाँ पे. देखो ये कोड फर्स्ट ऑफ ऑल बना हुआ है. यहाँ पे हम देखें तो ये मेट्रोड लैब है, हम इंपोर्ट किया हुआ है यहाँ पे फर्स्ट पैराग्राफ में. एंड द सेकंड वन इज दिस इज द बेल सर्किट. आपके पास बना पड़ा हुआ है यहाँ पे बेल स्टेट की जो मैं बात कर रही हूँ. ये बेल का सर्किट है प्रॉपरली. एक्चुअली फर्स्ट ऑफ ऑल पाइथन प्रॉपरली आपको आनी चाहिए. पाइथन के बिना ये रन नहीं होगा. पाइथन आपको कोरली आनी चाहिए, क्योंकि पाइथन का ही देखो यहाँ पे सर्किट है और सर्किट को इंक्लूड कैसे करना है, बेसिकली वही हमको इशू रहता है वहाँ पे. तो यहाँ पे अगर देखा जाए तो हमने ATAL स्टेट का आपने सबने वो देखा होगा, वो पोस्टर देखते हैं, उसमें एक हेडामार्ट होता है, एक सी नोट होता है। हेडामार्ट में क्या करते हैं हम, ये देखो यहाँ पे सर्किट है, सर्किट डॉट H0, दैट मींस हेडामार्ट हमारा 0 पे लगा हुआ है। ओके, एंड द कंट्रोल जो सी नोट गेट लगा हुआ है, सी नोट गेट में दो हमारे पास होते हैं, दैट इज द कंट्रोल एंड टारगेट। यहाँ पे देखो कंट्रोल जो सा 0 पे लगा हुआ है, टारगेट जो सा 1 पे। ये प्रॉपरली आपको समझना पड़ेगा, दैट उसके बिना ये चलेगा। उसके बाद ये हमारे पास अगर मैं बात करूँ this is the bell which we see in graphical way। ये प्रिंट हो गया क्योंकि प्रॉपरली आपने क्वांटम के थ्रू वो बना और हमारे पास 0 और 1 है, हेडामर्ट लगा, सी लगा वहाँ पे उसके साथ 0 पे, उसके बाद एक्स गेट लगा हुआ है। एक्स गेट आपको पता है किसके लिए यूज होता है, एक्स गेट फॉर कन्वर्टिंग 0 to 1। ओके, तो ये सारा पूरा बेल का लगा हुआ है। इसमें यहाँ पे हमारे पास लाइक अनदर थिंग ये ग्रोवर वगैरह के सारे एल्गोरिथम्स अवेलेबल हैं यहाँ पे। अगर देखा जाए तो अगर वहाँ पे आपने पढ़ने हो, या ग्रोवर सर्च एल्गोरिथम्स है एंड ऑल, सारा स्टफ यहाँ पे पढ़ा हुआ है पढ़ने के लिए। और प्लस इसका कोडिंग पार्ट भी आपको मिल जाएगा, सर्किट पार्ट भी मिल जाएगा। एम्पलीट्यूड एम्प्लीफिकेशन, ये तो हमारे मेजरली जो सी चीज़ें यहाँ पे सब पढ़ो। तो इसके लिए आपको फर्स्ट ऑफ ऑल आपको ये ध्यान में रखना है, लाइक अगर हम काम खत्म करते हैं तो आपको नोटबुक प्रॉपरली क्लोज करनी पड़ेगी। अगर आपकी नोटबुक चलती रह गई 2-4 घंटे भी रहेगी तो ये भी देगा चार्जेस, क्योंकि मेरे बड़े हुए हैं चार्जेस, मेरे को $50 पड़ गए थे। समझ सकते हो आप भी, सिर्फ मेरा 4 से 5 घंटे को नोटबुक चलता रहेगा। तो अगर वो एक दिन रह गया तो आप समझ सकते हो। नोटबुक चलने के भी पैसे हैं वहाँ पे, कुछ आवर्स के बाद वो पैसे डालने चाहिए। नोटबुक आपने काम खत्म किया नोटबुक में तो आपको यू हैव टू क्लोज द नोटबुक।
इफ वी लॉग आउट तो अपने आप बंद नहीं होती नोटबुक?
नहीं सर।
तो सर किस तरह करनी है बंद?
Here I have a notebook and यहाँ पे जाके and action,
keep on running in background.
action,
Smart way to earn money.
गुड देयर इज स्टॉप बटन, स्टॉप से बंद हो जाएगी। ठीक है, आप देखो जो मैंने पहले बनाई थी वो रनिंग में आ गई, ये रनिंग में आ गई हमारी, और वो 10 से 15 मिनट रनिंग में लेने के लिए ही मेनली अमेजोन अवेलेबल तो है, वर्किंग भी ठीक है, बट इसमें पाइथन मेजर रोल है। अगर आपको पाइथन नहीं आता तो आप इस पर वर्क नहीं कर सकते। पाइथन जरूरी है इसके लिए, जो फिजिक्स बैकग्राउंड से है या मैथमेटिकल बैकग्राउंड से है उनके लिए मेजर हर्डल वही है। अगर देखा जाए तो अभी करिकुलम में पाइथन आया, पहले पाइथन करिकुलम में भी नहीं था कंप्यूटर साइंस वालों के भी, तो दिस इज अ मेजर इशू फॉर कंप्यूटर फॉर पाइथन necessary. Okay, this is for Amazon and this is Composer, IBM Composer. This is represent with graphically, आपको दिखेगा गेट कहाँ पे बन रहा है विदाउट कोडिंग, यू नो ड्रैग एंड ड्रॉप जो जावा में हम करते थे पहले, ड्रैग एंड ड्रॉप का कंसेप्ट है। हेडामार्ट की बात करते हैं हम, हेडामार्ट सबने सुना होगा, हेडामार्ट गेट। एंड अगर मैं यहाँ से सिर्फ ये हेडामार्ट हमारा और ये हेडामार्ट अप्लाई हो गया, साथ साथ में विजुअलाइजेशन दे रहा है। इसमें अगर मैं बात करूँ जो सा ये क्यूबिट है, ये दैट वन क्यूबिट है, ये बेसिकली शुरू से 0 बाय डिफॉल्ट इट्स 0। अगर आपको इंक्रीज करनी है क्यूबिट इस कोड में जाके, तो जितनी है दैट हेयर 1 है, तो मैं 2 ऑटोमेटिकली ओके, एंड डिलीट पे सीधा डिलीट हो जाएगा। ठीक है, एंड अगर मैं बात करता हूँ this is the interface when you have to sign in. It is free, but there is some shorts available, but इसमें नोटबुक वाला कोई इशू नहीं है, इसमें फ्री है और आप आराम से कर सकते हो इसको। बट इसमें ये रहता है भी जब आपके एल्गोरिथम हैवी हो जाते हैं, लाइक हम काफ़ी गेट्स यूज करते हैं, तो दैट वो अप्लाई नहीं कर सकता, इसमें ये रहता है। ये क्वेश्चंस हैं जो मैं हैंड्स ऑन में करवाने वाला था, अभी चलो मैं अपने आप ही करके दिखा देता हूँ आपको वैसे तो। ठीक है, ये बेसिकली क्वेश्चंस है। फर्स्ट क्वेश्चन हमारे पास है टू स्टेट मेक करना 1 बनाना है, क्योंकि बाय डिफॉल्ट ये 0 है, बाय डिफॉल्ट 0 है, क्योंकि हमको वहाँ पे कहीं ना कहीं चाहिए 0 से 1 होने के लिए, तो उसके लिए बेसिकली ये फर्स्ट कैसे बनेगा, ये है हमारा आउटपुट साथ में दिखाएगा। लाइक मैं आपको चला के बता देता हूँ। दिस इज द एक्स गेट, दैट वन एक्स गेट, एक्स गेट बोलते हैं इसको। एक्स गेट क्या करता है, इज अ लाइक नॉट गेट, इट्स लाइक 0 को 1 1 का 0 एक्स गेट। तो इसमें क्या है, यहाँ पे आउटपुट आप देख सकते हो नीचे। एक्चुअली ये लोकल सिमुलेटर पे वर्क कर रहा है, जो आपको आउटपुट दिखा रहा है ना, लोकल सिमुलेटर पे। इसको अगर आप रन करना चाहो तो ये यहाँ से सेटअप है हमारा, सेटअप एंड रन, ये ये लोकल सिमुलेटर है इनका। ठीक है, यहाँ पे रन कर सकते हो आप। ठीक है, शॉर्ट यही रहने देना, कोई इशू नहीं है। 1024 इज अ बेसिक शॉर्ट, एक बार में चलने के लिए इतना रहते हैं। ठीक है, ये अलग अलग क्वांटम कंप्यूटर जो IBM अवेलेबल करवाता है, ये सिमुलेटर स्टेट वेक्टर है हमारे पास। अगर मैं बात करूँ ऊपर हमारे पास है MPS है, स्टेबलाइजर है, उसका है। ठीक है, देयर आर ये हमारे ऑनलाइन क्वांटम कंप्यूटर अवेलेबल है, ये वो है। इस पे रन करोगे, देयर इज अ नॉइस, देयर इज समथिंग, जैसे अभी सर बता रहे थे, वहाँ पे नॉइस का इशू रहता है, वहाँ पे यानी कोई भी इशू हो सकता है, लाइक नेटवर्किंग ठीक नहीं है या कुछ नहीं है, तो वो इशू यहाँ पे रहता है. दैट मीन्स प्रोबेबिलिटी अगर मैं बात करूँ नॉर्मली यहाँ पे आ रही है मेरी 1/2 एंड 1/2 हाफ आ रही है प्रोबेबिलिटी यहाँ पे इन आउटपुट्स में. और अगर आप क्वांटम वाले पे जा रहे हो वहाँ पे 1/2 इक्वल नहीं आएगी. वहाँ पे इशू ये रहता है नॉइस आ गया बीच में या समथिंग एल्स कुछ भी एरर आ गया तो वो 1/2 इक्वल डिवाइड नहीं करता.
Amazon AWS पे था ना ऐसा एक program?
यस सर, वो हमारा बेस्ट स्टेट हम बनाते थे, जब बेस्ट स्टेट तैयार के देखते थे हम.
यहाँ पे है
हाँ सर चला रहा
जो प्रोबेबिलिटी डिफरेंट आती है जो.
हाँ जी सर.
You mentioned a local simulator. What does it mean, local simulator?
सर ये सर्किट हमारा यूज करता है, ये क्लासिकल कंप्यूटर यूज कर रहा है हमारा.
वो आपका लैपटॉप यूज हो रहा है?
हाँ.
तो क्लाउड यूज नहीं हो रहा. हाँ, इस पे
प्रोसेसर आपका
लोकल प्रोसेसर.
ये प्रोसेसर यूज हो रहा है कि वो सिमुलेटर आपके लैपटॉप पे इंस्टॉल्ड है?
ना 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 सर, कोई इंस्टॉल नहीं है हमारा. एक्चुअली ये एक जो है इंटरनेट अवेलेबल होना चाहिए इसको चलाने के लिए. पहले तो
हाँ हाँ.
इंटरनेट अवेलेबल है तो ये रन करेगा, और वो जो सर्किट उसको चाहिए वो हमारे पीसी पे यूज करेगा, वो बाहर कहीं नहीं करेगा.
जस्ट लाइक अ सॉफ्टवेयर सर, ऑनलाइन अवेलेबिलिटी.
Online
सॉफ्टवेयर है, इंस्टॉल हो जाएगा हमारे सिस्टम के ऊपर.
हाँ.
उसको रन करने के लिए इंटरनेट चाहिए.
तो बिना इंटरनेट के नहीं चलेगा?
नहीं. इंटरनेट इज अ मेजर.
Amazon AWS पे वो प्रोबेबिलिटी डिस्ट्रीब्यूशन.
हाँ देख लेता हूँ सर. ये मैंने बंद कर दिया एक्चुअली ना, वो दोबारा से रन करेगा.
ये कुछ कह रहे थे आप डमी डेबिट कार्ड, वो क्या चीज़ होती है?
सर इसमें है डेबिट कार्ड. डेबिट कार्ड का मतलब ये है वो जस्ट फेक है. आपके पास डेबिट कार्ड तो है क्रेडिट कार्ड से, बट उसमें आप अमाउंट दे रहे हैं. उसमें ये सेफ्टी रहती है आपके पास कि अगर आपने वो लगा दिया तो वो आपका यानी कि ना पेमेंट नहीं कटेगी. वो आपको मेल भेजते रहेंगे,
स्टेप अहेड.
मेल भेजते रहेंगे भी हाँ यू हैव टू पे. बट अगर आपकी मर्जी है तो पे कर दो, नहीं तो नया अकाउंट बनाओ, नया रन करो.
मतलब साइन अप पे वो यूज होएगा?
हाँ जी साइन
Kind of sign up हो।
क्रेडेंशियल्स देने पड़ेंगे. जैसे नेटफ्लिक्स पे
बेसिकली
वगैरह
डमी
देते हैं
मीन
credentials.
दैट इज ए रियल डेबिट कार्ड.
रियल डेबिट कार्ड.
मान लो उसमें बैंक के साथ आपके कनेक्टेड था, तो जब किया आपने तब तो वो कुछ करेगा ना, ट्रांसफर करेगा.
No,
तब पैसे होने चाहिए.
1 रुपीस.
हाँ, 1 रुपया कुछ भी है.
Only 1 रुपीस.
हाँ.
1 रुपीस भी कटा नहीं था मेरा.
नहीं, वो तो वापस आ जाता है, कट के
हाँ,
वापस आ जाता
कट
है.
के वापस आ
हाँ,
गया.
वापस आ जाता है वो.
वो एक्चुअली क्रेडेंशियल लेते हैं, वो
हाँ,
ये
credential.
देखते हैं वो डेबिट एग्जिस्ट करता है
दे
कि नहीं.
वेरीफाई अकाउंट, दे वेरीफाई
हाँ दे वेरीफाई अकाउंट.
अकाउंट. मगर डेबिट कार्ड तो ओरिजिनल होगा ना, सही
हाँ
होगा.
डेबिट सर ओरिजिनल.
तो फिर डमी कैसे बनाओगे उसका अकाउंट में से?
पैसे नहीं रखते ना.
अकाउंट में पैसे बंद करवा दो वो
नहीं रखने.
अकाउंट.
नहीं रखने.
फिर-
अगर पैसे रखेंगे सर वो
अरे अरे फिर बैंक पैसे चार्ज करेगा आपसे.
डेबिट कार्ड हाँ
मैं बैंक चार्ज करूंगा, बैंक मिनिमम अमाउंट मेंटेन करना पैंदा उत्थे.
सर 50 से 60 रुपए होते हैं उसमें.
होता है अमाउंट होता है.
हाँ 50 से 60 रुपए रखे हुए हैं. तो
जीरो बैलेंस से भी खुल जाते हैं।
होता है, सब कुछ होता है.
ਵੈਸੇ ਅੱਜ ਕੱਲ ਕਾਰਡ ਵੀ ਆ ਰਹੇ ਆ ਜੇ ਕਾਰਡ ਤੇ ਜਾਓ ਤੇ ਕਾਫੀ ਅਵੇਲੇਬਲ ਹੈਗੇ ਜੇ ਤੁਸੀਂ ਬਲੈਕ ਮਾਰਕੀਟ ਦੇ ਵਿੱਚ ਵੀ ਦੇਖੀਏ ਤੇ ਡੈਬਿਟ ਕ੍ਰੈਡਿਟ ਕਾਰਡ ਵੀ
वो एक अलग मार्केट है.
ਮਾਰਕੀਟ
एक अलग मार्केट है डमी क्रेडिट कार्ड.
ਉਹ ਪੇਪਾਲ ਦੇ ਮਿਲ ਜਾਂਦੇ
ਜਿਵੇਂ ਈਮੇਲ ਵੀ ਮਿਲਦੇ ਸੀ, ਤੂੰ ਈਮੇਲ ਬਣਾਣੀ ਕੋਈ ਬਣਾ ਲਓ, ਕੁਝ ਚੱਲ ਰਹੀ ਡਿਸਪੋਜ਼ੇਬਲ ਈਮੇਲਸ.
ਜੀ ਜੀ
ਡਿਸਪੋਜ਼ੇਬਲ ਡੈਬਿਟ ਕਾਰਡ ਆ ਜਾਣੇ ਫਿਰ.
ਸਰ ਉਹ ਤੇ ਇੱਕ ਮੇਰੇ ਖਿਆਲ ਸਾਈਟ ਤੋਂ ਸਟੂਡੈਂਟ ਬਣਾ ਰਹੇ ਸੀ ਉਹ ਅੱਜ ਕੱਲ ਆਨਲਾਈਨ ਚੱਲ ਮਤਲਬ ਕਿ ਹੈਗਾ ਵਾ ਕੁਝ ਹੈਗਾ ਵਾ ਟੈਂਪਰੇਰੀ ਟੈਂਪ ਈਮੇਲ ਦੇ ਨਾਮ ਤੇ ਕੁਝ ਹੈਗਾ ਤੁਹਾਨੂੰ 10 ਮਿੰਟ ਵਾਸਤੇ ਤੁਸੀਂ ਜੋ ਮਰਜ਼ੀ ਵੈਰੀਫਾਈ ਕਰ ਲਓ ਜੋ ਮਰਜ਼ੀ.
डिस्पोजेबल ईमेल.
डिस्पोजेबल ईमेल हैगी है.
बहुत कुछ है.
And the next question is,
Are there some simulators available which we can install on our labs for which no internet is required? But they are
sir,
really on your
actually
computer.
all the simulators are cloud based. Not actually there is no hardware available. You say that some hardware. and
Simulator is a software.
Simulator actually cloud simulator available. Only.
वो open source कोई नहीं है.
Oh, yeah, but cloud.
नहीं है. Open source cannot be on cloud. It can be on my hard disk on my computer.
There is not available.
Open source means that source code is available. I can compile it and run it on.
No, sir, there is not available. only cloud.
Open source, no open source is very
No.
good.
सर इसमें क्या है कि कुछ जैसे
ओपन सोर्स की डेफिनेशन कुछ और है ना.
इसमें जो दो तरह के सिमुलेटर है ना, इसमें भी बताया जैसे कुछ क्लाउड वाले हैं,
हाँ।
कुछ लोकल पे चलते हैं, लेकिन उनका इंटरफेस सेम है. मतलब कहने का मतलब है व्हेन वी एग्जीक्यूट इट इज अप टू अस वेदर वी वांट टू रन ऑन अ लोकल सिमुलेटर और वी वांट टू रन ऑन अ क्लाउड सिमुलेटर. जैसे इस केस में ये लोकल सिमुलेटर को रन कर रहा है जो कि यहाँ पे है. अभी इसने ऑप्शन दिखाया था जिसमें क्लाउड सिमुलेटर जो क्वांटम हार्डवेयर है वो ऑनलाइन है अवेलेबल.
What I understand, although terminology जो मर्जी बोलते जाएं, without internet you can't use it. Right? Mean they are using your resources. That's the smartness.
This is next one. The next question is make state 1 by 2, 1 by root 2, 0 plus minus 1. There is available 1 plus or minus. Both are available. And the output is this. It is for 0 plus 1, 1 by 2. Actually, there is a two thing. If we apply the Hadamard on 0,
जब
it
बोल के
gives
उसकी
us.
स्टेट कैसे चेंज की थी आपने फर्स्ट की?
Okay. Sir, actually there is a gate only.
हाँ?
Plus X gate.
तो गेट से चेंज हो गई ना?
हाँ जी sir. This is the gate we use. X. That one gate we use. And the output
तो
is
इसकी
0 to.
ये लैंग्वेज कौन सी है?
हाँ जी sir.
ये राइट हैंड साइड पे जो लैंग्वेज लिखी आ रही है ये कौन सी लैंग्वेज है?
लैंग्वेज नहीं है कौन सी ये वाली सर.
हाँ हाँ.
सर ये कोड है एक्चुअली फॉन्ट लैब का कोड है. ये जस्ट नॉर्मल है, पाइथन में नहीं होता ये प्रॉपर. इसमें पाइथन के अलग से आपको ऐड करने पड़ते हैं. ये क्वांटम का ये बता रहा हूँ भी आपको कौन कौन से यूज कर रहे हो उसके गेट. यहाँ पे फंक्शनैलिटी क्वांटम की कौन कौन से यूज कर रहे हो. यहाँ पे जैसे मैंने क्यूबिट यूज करी है.
सर जी जैसे qubits.inc फाइल है.
हाँ जी सर.
ये अपने आप इंक्लूड होगी ना?
आप पे बाय डिफॉल्ट यही है.
नहीं, we use include in C.
हाँ.
It might be C or C++. Syntax example to C.
सर एक्चुअली बेसिक का उत्थों ही चल जाता है.
क्यू हैश
बेसिक का उत्थों ही
क्यों
है.
है?
हाँ,
क्यू हैश कहते हैं आईडिया और नवी दी हुई है.
यूज करा हुआ है सर उन्होंने, बट तो वो चीज़ नहीं है कि जो
जैसे वो सिंबॉलिक रिप्रेजेंटेशन है फिलहाल.
प्रोग्रामिंग ਹੁੰਦੀ ਹੋਰ ਕੀ ਹੁੰਦਾ ਹੈ? इट्स प्रोग्रामिंग.
एक्चुअली सर जब रन करते हैं ना आप लोकल सिमुलेटर पे कोड देना ना.
ठीक.
The next one is for Hadamard. Hadamard. We apply the Hadamard and then the probability is 50-50. 50 for 1, 50 for 0. It is for in a broad sphere, Q sphere, there is a 0 and they are pointing to 0 and 1, and both are positive. They are not changing their phase. 0 and 1, positive, impossible. If we apply with the Z gate, there the color is a change. That means the phase is changed. It is in now minus state. The next question is in 0 minus 1. That about second equation. First is 0 plus 1 and the second is 0 minus 1. This is the second equation. Where it change the phase. Actually, all the gate, अगर आप gate properly आने ये properly सीखना. जो सा ब्लोच होता है आपका, ब्लोच स्फीयर clear होना चाहिए आपको एक एक. And the next question is. This is the next question. Where we use root 3 by 2. Half तो 1 को दे दी, but 3 by 2 हमने 0 को दिया. Probability distribute 50-50 नहीं कर सकते, अलग कर. उसके लिए क्या करना? we apply RY gate, rotation to Y gate, rotation to Y axis. Here the value is pi by 2. Here the value is pi by 2. If we convert the value, then the probability will change. Otherwise, it divided into simple 50-50%. Here, added the value. We added the value and give it as a pi by 4, and the output is different now. 85
एडिट कैसे किया आपने?
Yes sir.
एडिट कैसे?
Right click.
Right click and edit option. Okay. The next one for negative, change the plus sign to negative, and we use for Z gate as change the phase. Okay. अब चला के दिखाना है ये?
ना ठीक है.
Okay.
Time.
This is for iota. Iota used in some gates. You know that? Iota in which gate? Phase gate. Phase gate. Phase gate. Yes. Phase gate. But phase for changing phase, no? Changing the phase. Actually, phase gate is majorly used in physics department. Physics department, we are not that much used in computer science. Here, we have to write it as a root 3 by 2, 0 plus iota by 2, 1. And we use Z as change the phase. Change the phase is the negative value. It's a negative value or not? Like that. If you use the negative, this changes into another circle. Like it. Okay. You change only the phase with the rotation of y and pi by 3 with the help of phase gate. There is some question for you. All you know about what is H and X gate now? पता ही चल गया. अगर मैं बात करूँ H X H is equal minus Z. Z क्या कर रहा था? हमारा फेज ही चेंज कर रहा था. नेगेटिव टू पॉजिटिव, पॉजिटिव टू नेगेटिव. दैट्स इट. अगर मैं तीनों लगाता हूँ तो मे बी लेट्स ट्राई. What it did? It gave an answer with 0 only. Only 0. We applied 2 Hadamard and 1 X. What Hadamard did? Hadamard take from 0, converting into 1 by 2, 0 plus 1, 1 by 2, 1. And then x, but x did 0 to 1. First 0 converted to 1, and another second 1 converted to 0. And then Hadamard comes, it also gives us if there is a, 2 Hadamard, what did 2 Hadamard? What 2 Hadamard did? Nothing.
Back to square one.
एक्चुअल हेडामार्ट फर्स्ट वाले ने सुपरपोजिशन बनाया, दूसरे वाले ने इसको कैंसिल कर दिया, तो वो 0 का 0 रह गया. ओके, तो ये हेडामार्ट अगर दो इकट्ठे लगे हुए हैं तो वो कुछ काम नहीं करेगा, तो 0 भी रह जाएगा. एक बनाएगा, दूसरा उसकी सुपरपोजिशन तोड़ देगा. तो अगर इसके बीच में मैं एक x लगाता हूं तो भी कुछ नहीं हो रहा, वो 0 पे रह रहा है, बिकॉज ऑफ x ने कुछ नहीं किया, x ने सिर्फ 0 का 1 किया, क्योंकि हेडामार्ट को 0 और 1 चाहिए कहीं ना कहीं, है ना. तो सुपरपोजिशन चाहे आगे 1 रख लो चाहे पीछे 1 रख लो, इधर सुपरपोजिशन, तो वो वापस वहीं पे 0 पे आ गया. तो इसको मैं नेगेटिव z के इक्वल नहीं बोल सकता, क्योंकि z क्या करता है, फेस चेंज करता है, नेगेटिव में जाएगी वैल्यू, नेगेटिव में तो जानी थी, 0 का था 0 पे स्टेबल. ठीक है. And the next one is h by h. h by h. ये ट्राई करते हैं. What it did? 0 to 1. अगर मैं इसके इक्वल देखूं, ये हमारे पास फेस भी चेंज है, अगर देखा जाए फेस ऑल्सो देयर है, नेगेटिव में है ना, नेगेटिव में है ना पहले. तो अगर मैं आउटपुट क्या लेने थे मैंने, इसके इक्वल माइनस वाई, तो वाई क्या दे रहा मेरे को, वाई क्या दे रहा, 0 to 1 कर रहा और फेस भी चेंज कर रहा है ना. दैट मीन्स अगर मैं y रखूं, 0 वैल्यू दी मैंने सिंगल y को, सिंगल वैल्यू दी y को, 0 वैल्यू दी है, वो क्या कर रहा, फेस कन्वर्ट करके और 0 to 1 भी कर रहा. दैट मीन्स x क्या करता था हमारा, 0 to 1 करता था, बट y क्या करता, फेस भी चेंज कर देता और वैल्यू भी चेंज करता, दोनों चीजें कन्वर्ट कर देता. क्या हम इसको इक्वल बोल सकते हैं दोनों को? कौन सा अभी देखा, इक्वल बोल सकते हैं, इट्स इक्वल. यस. Okay, next one, h t t h and rotation to x pi by 4. H t t h. First, you have to know what the t did. What t single did? Nothing. Now we apply Hadamard 1. Second Hadamard 1. What it did? It not convert the 1 by 2, 1 by 2. It's not in 1 by 2, 1 by 2. The probability of 0 is 85 and the probability of 1 is 14, nearby 14. Okay, and the another side is Rx pi by 4. Look at that. Pi by 4. Rx, but the value is pi by 4. Is equal. It is equal. There is a 3 gate, there is a 1 gate. This is the reason why we use rotation of x gate, rotation of y gate. This is the reason. Here probability of 0 is 85 and probability of 1 is nearby 50. Okay. The next is HZH. What Z did is convert the phase. Only one. With converting the phase. Actual when first Hadamard works, it converts into superposition, that is 0 plus 1. When that are there, they are converting with the number minus to 1 plus. माइनस टू प्लस, तो उसके बाद जब दूसरी वाली जब सुपरपोजिशन बनाएंगे तो माइनस कॉमन आएगा, तो उसकी वजह से ये 1 आउटपुट आएगी, क्योंकि जो सी सुपरपोजिशन बाहर आएगी नेगेटिव में आएगी और 1 की वैल्यू देगी। क्योंकि जो सा सुपरपोजिशन हमारे पास होता है 0 में, सुपरपोजिशन के अंदर 0 जो सा होता है वो पॉजिटिव वाला होता है और 1 जो सा होता है वो नेगेटिव वाला होता है। ये मैथमेटिकली आप सॉल्व करोगे तो आपको मैथमेटिकली क्लियर करना पड़ेगा, सुपरपोजिशन तोड़नी पड़ेगी आपको। ठीक है, इसके इक्वल कौन सा था? x था, सिंगल x। सिंगल x में तो हमारा 0 to 1 होता ही, आपको बताइए क्या हुआ। ओके, सिंगल x लगाता हूँ तो वो 1 होता। This is all operation we did on single qubit. Single qubit पे हमने काम किया। अब next move on करते हैं।
सर इसमें जो लैब वाला पार्ट था, कंपोजर के साथ लैब है ना,
कहाँ पे सर? कंपोजर में
लैब लिखा हुआ है कंपोजर के साथ।
हाँ जी सर,
कंपोजर के साथ।
हाँ जी सर, वो कोडिंग
अमेज़न जैसे कर रहे हैं।
हाँ, सेम अमेज़न वाला काम, कोडिंग वाला।
उसमें सो पाइथन की कोडिंग।
पाइथन की कोडिंग
ये फ्री है इसमें, ये फ्री है तो फिर अमेज़न की तो फिर उस टाइम नहीं है।
सर एक्चुअली they providing another quantum computers. IBM provided another quantum computers. This is the reason.
As a
काम कर
we can use.
We can use.
We need to spend as.
But actually सर अगर आप कोड करोगे, अगर बेसिक फंक्शनैलिटी समझनी है गेट्स वगैरह की या कोई पर्टिकुलर एल्गोरिथम की बेसिक फंक्शनैलिटी समझनी है तो ये हमारे पास अवेलेबल है। बट अगर हम बात करें, हम कोड में जाते हैं, कोड में हम अपना एल्गोरिथम क्रिएट करेंगे, है ना? तो अपना जब क्रिएट करेंगे तो वो बड़ा बनेगा, बड़ा बनेगा तो शॉर्ट्स ज्यादा होंगे।
इसमें भी
तो पैसे ले लेगा,
सेम।
नहीं पैसे ले लेगा जी।
हाँ जी सर,
तो पैसे ले ले, फिर उसमें क्या होगा?
मतलब इसमें ज़्यादा फ्री है ना, मतलब अमेज़न तो।
हाँ सर, अमेज़न तो बिल्कुल ही चार्जेबल है। इसमें जो सी हमारी आईआईटी विदाउट डेबिट कार्ड बन जाती है।
हाँ, वो
दिस इज द मेजर इशू।
जब स्टूडेंट को गाइड करेंगे तो
हाँ,
ऐसे गाइड
ये
कर सकते हैं ना, तो
लर्निंग के लिए ठीक
ठीक
है।
है।
वंस यू हैव सम प्रोजेक्ट देन यू कैन पे, तो पेमेंट कोई नॉमिनल होगी, बहुत ज़्यादा होगी नहीं।
यस सर।
सर आप इसमें कुछ रियल प्रोग्राम भी करवाओगे कि कोई प्रॉब्लम सॉल्व करनी है अपने क्वांटम ऐसे की? ये तो बड़ा बेसिक फंडामेंटल ऑपरेशन हो गया ना। ये तो
प्रॉब्लम जो सी सॉल्व करने वो मैथमेटिकली सॉल्व होती है, सुपरपोजिशन, देन हम अंडरस्टैंड करते हैं इसके। ये तो ग्राफिकली तो मैं दिखा दूंगा, बट वो
नहीं, आइदर ऑन अमेज़न ऑन हियर कैन आई सी एनी रियल प्रॉब्लम सॉल्विंग कि देखो ये हमने प्रॉब्लम सॉल्व किया है,
क्लासिकल में नहीं कर सकते।
लेट अस से नहीं, चाहे कर भी सकते हो, वी वांट टू सी हाउ थिंग्स वर्क ऑन क्वांटम। बहुत बड़ी बात हो जाएगी ना, उसी को कर दें, पर उसमें पता चले कि चीजें होती कैसी हैं।
एक्चुअली अभी तो हम तो बिगिनर हैं।
नहीं, लेट अस से कैन वी हैव समथिंग लाइक 2 + 2 4 बता दीजिए। जैसे हेलो वर्ल्ड प्रोग्राम होता है ना, तो क्वांटम कंप्यूटर में हेलो वर्ल्ड प्रोग्राम कैसे होते हैं?
सर वो एक्चुअली ये मैं दिखा रहा हूँ सुपरपोजिशन कन्वर्ट कैसे हो रही है। सुपरपोजिशन इज द बेसिक थिंग्स देयर,
मतलब गेट्स कन्वर्ट कर रहे हैं।
ये तो हमें समझ नहीं आएगी।
वेल स्टेट तो आगे आएगी। हां, एंटेंगलमेंट की वेल स्टेट है वो बता दूंगा सर आगे।
नहीं, मेरा क्वेश्चन कुछ और तरह का है।
आप
Okay.
रियल टाइम पे जा रहे हो ना।
मैं तो कोई प्रोग्राम
नहीं वो कह रहे हैं सीधी ਵਿੱਚ ਅਸੀਂ printf ਲਗਾ ਕੇ hello world
सर आउटपुट सर आ रही है इतने जस्ट प्रोबेबिलिटी है।
This is mainly on
बस।
0 and
इसको यूज कहाँ करेंगे फिर हमें कुछ समझ नहीं आया क्योंकि आई मीन वी हैव टू यूज इट
सर आपका क्वेश्चन बिल्कुल वैलिड है।
हाउ टू यूज इट एंड वी हैव टू यूज इट
उसका कोड एग्जीक्यूट करके बता देना।
सर वो एग्जीक्यूट होगा तो वो दिखा देगा, वो जस्ट जैसे वेबसाइट दिखाई है अभी दिखा
नहीं यू कैन टेल अस कि वो किस प्रॉब्लम को रिप्रेजेंट करता है, अभी कौन सी प्रॉब्लम हम सॉल्व कर रहे हैं।
एंटेंगलमेंट सर वेबसाइट का भी मैं दिखा देता हूं सर, मैं वेबसाइट में इसी कंपोजर में काम कर रहा हूं वेबसाइट।
जैसे मैं कहूँ टेम्परेचर कन्वर्ट करना है, यू टेल मी कि दिस इज अ प्रोग्राम व्हिच कन्वर्ट्स द टेम्परेचर।
जस्ट एन एग्जांपल।
This is the website used for entanglement.
डिफरेंट वेबसाइट AWS में एल्गोरिथम है वो एग्जीक्यूट हो जाएंगे अभी तो जो शोज का एल्गोरिथम है
कहीं पे दिखा दीजिए।
वो कॉपी करके इसकी लैब में चला दो, चल जाएगा।
हाँ चल जाएगा।
AWS की जो हमारे पास इसका एल्गोरिथम है जो इनबिल्ट एल्गोरिथम है ये काउंटर है ना जो ऊपर प्रोबेबिलिटी है
सर ये मैं प्रिंट कर
इसमें डिवाइस की शॉर्ट्स क्या है, इसमें प्रोबेबिलिटी कैसे हुई,
सर हियर इज बेल सर्किट का यहाँ पे प्रोग्राम है सर। ये हमारा एक बेल बना, बेल के अंदर ये लोकल सिमुलेटर डिवाइस लोकल सिमुलेटर पे चल रहा है, ठीक है। तो ये रिजल्ट शॉट्स 1000 लगे हुए हैं यहाँ पे, 1000 शॉट्स लगे हुए हैं, दैट मीन्स वर्किंग फॉर 1000 मिनट सेमी मिनट वो और रिजल्ट प्रिंट कर रहा है।
तो काउंट क्या डिनोट करता है?
काउंट यहाँ पे ये डिनोट कर रहा है 1 जो सा हमारे पास है उसकी प्रोबेबिलिटी 5, दैट मीन्स 1 अक्कर हुआ 503 बार 503 टाइम्स एंड 00 अक्कर हुआ 497 टाइम्स।
लाइक जैसा हेड और टेल वाला से एक्सपेरिमेंट कर दिया और 1000 टाइम्स
Yes.
कर दिया।
1000 टोटली हमारा 1000 बार चलाया उसको और वो क्या 11 जो सी है 11 की आउटपुट 503 आई और 00 की 400।
दोबारा रन कर,
दोबारा मैं चेंज कर देता हूँ
इसी को रन कर दोबारा,
इसी को रन
हाँ एग्जीक्यूट कर दोबारा।
ओके सर चेंज हो गया सर,
फाइल वैल्यू चेंज
हो गया सर बिकॉज ऑफ द नॉइस एंड द अदर जो इसको अभी क्वांटम जिस पे काम करते हैं जो अदर सोर्सेज है जो इसको हेजिटेट करते हैं प्रॉपरली वर्किंग करते हैं, वो नॉइस हो सकता है, वो अनदर कोई इंफ्रास्ट्रक्चर इशू हो सकता है, कोई वेव हो सकती है,
कुछ
कुछ
लोकल सिमुलेटर को भी रन कर रहे हैं ना।
हाँ जी सर,
लोकल सिमुलेटर तो तेरे सिस्टम के ऊपर रन कर रहा है,
हाँ जी सर।
फिर
But
सिस्टम में जो
actually-
नॉइस है वो कहाँ से आएगी?
Actually, sir, the probability is not for 50-50 exactly. The thing is that क्योंकि वहाँ पे रीजन रह रहा है, this is for the quantum is not properly working now. वो जो सा इशू रह रहा है वो 1 से 2% एक मिलीवन, जैसे अगर मैं बात करूँ नॉट 51 50-50 इज 51 और 49 इज 47 और 52 वो इशू रहेगा।
सर अगर शॉर्ट्स इंक्रीज कर देंगे
शॉर्ट इंक्रीज कर देंगे तो वो वैल्यू चेंज होगा।
10,000 कर देंगे।
हाँ मेरा काम है।
ऐसे लगता है
I'm trying to correlate it with classical things.
100 करके तो
10 कर लो यार, 10 कर ले।
100 चेंज किया तो 53 फुट से हम मैक्सिमम हम 1000 तक चलाते हैं, उसकी ज्यादा हम इंक्रीज खुद नहीं करते।
Classically what happens that as the number of trials increase, then probability comes equal to threat. So that's why I said कि अगर उन्होंने increase करिए तो quantum mechanically वो threat।
क्वांटम मैकेनिकल मैम ये बेल स्टेट में ये बता रहा है अभी दोनों के पास, हमारे पास दोनों के पास कंट्रोल है। ये एंटेंगलमेंट की पोजीशन सॉल्व कर रहा है बेल बस।
और सर ए वाला सेम कोड वाली लैब से चलेगा थोड़ा IBM वाला।
मैं मूर्ति में चलाया
सर हम कर लो ट्राई।
जो थ्योरेटिकली फिर एंटेगलमेंट से बराबर होना चाहिए थी ना।
बराबर आते हैं
नॉइस करने की वास्तव में
बराबर सर कितने भी नहीं आएगा।
तो थ्योरेटिकली मैं कह रहा हूँ, थ्योरेटिकली
बराबर।
अगर शॉर्ट्स को ज़्यादा इंक्रीज करेंगे तो वो पेमेंट का इशू कंस्ट्रेंट रहेगा ना।
सेम सर जो है वहाँ पे ये IBM लैब ओपन किया है, सेम इंटरफेस है, सब सेम है। पाइथन 3 से चलता है, वहाँ पे अलग दिया हुआ है।
पाइथन 3 में चला के देख लेना। सोर्स डिफरेंट आ गया ना।
सोर्स डिफरेंट है,
So just so command from graphics input.
डिफरेंट।
तो यही बात कर रहे थे ना सर वेंडर लॉकिंग की, वी हैव टू डिपेंड अपॉन द स्पेसिफिक प्लेटफॉर्म। But for the learning purpose, I think IBM quantum learning is good for the students. और अगर हमने सेल्फ लर्निंग करनी तो AWS is good. मतलब अगर आपको मतलब डिटेल में देखना है, बिकॉज दैट इज मोस्टली जो IBM वाला है दैट इज मोस्टली GUI बेस्ड एनवायरनमेंट, और AWS है वो थोड़ा कोडिंग बेस्ड आ जाएगा, तो थोड़ा डिटेल में आपको अंडरस्टैंड आ जाएगा कि हाउ द शॉर्ट्स आर एग्जीक्यूटिंग एंड ऑल दैट। बट उसके लिए आपको डमी अकाउंट बनाना पड़ेगा।
ट्रांसलेट कन्वर्ट कर सकते हैं हम लाइक में। चीज हो जाएगा इसमें, अगर डेटा था ट्रांसलेट 4 पार्ट्स में आता है। यहाँ पे 1 is for 00 and 01 and 10 and 11. This is for 10. This is 1 and here, and this is for 01. We add that one also there, and this is for 1. तीनों इसके लिए जरूरी होता है बेल स्टेट के लिए। तीनों तो हमारे पास ये तीनों अंडरस्टैंड करना ज़्यादा जरूरी होता है फॉर बेल स्टेट। हियर सी नॉट गेट में हमारे पास ये दो हमारे पास एक ऐसा गेट है जो दो क्वांटम पे क्यूबिट पे चलता है। फर्स्ट इज फॉर 0 0। ये जो सी मैट्रिक्स आप देख रहे हो, मैट्रिक्स अगर आपने मैट्रिक्स अंडरस्टैंड करनी है उसका सबसे बढ़िया तरीका ये रहता है कि आप यहाँ पे 0 0 ले लो, 0 1 1 0 एंड 1 1। इसको स्टेट को ले लो 0 1 2 3, ठीक है। तो ये क्या करता है, जब 0 0 होगा दैट मीन्स इसमें क्या होता है, कंट्रोल एंड टारगेट वाला सिस्टम होता है। कंट्रोल वाला होता है, कंट्रोल अगर 0 है तो टारगेट में कोई चेंज नहीं आएगा, ठीक है। तो अगर मैं इसकी बात करूँ, यहाँ पे 0 0 था, आउटपुट भी 0 0 है, कोई चेंज नहीं हुआ। यहाँ पे हमारा कंट्रोल 0 है तो आउटपुट भी सेम आ गई, कोई चेंज नहीं है। यहाँ पे हमारा कंट्रोल जो सा 1 है और टारगेट 0। कंट्रोल अगर 1 है हमारे पास तो टारगेट शिफ्ट कर जाएगा, वो घूम जाएगा, दैट इज 0 to 1 और 1 to 2। यहाँ पे हमारे पास टारगेट कंट्रोल हमारे पास 1 है, टारगेट 0 है एंड दैट इज 1। both are and here 1 is for control and 0 1 for target, वो टारगेट फिर से शिफ्ट। यहाँ पे अगर मैं देखूँ ये हमारा जो सब 1 1 होता है, बट सी नोट में ये टूट जाता है। क्यों टूटता है? द रीजन इज दैट क्योंकि यहाँ पे अगर मैं बात करूँ, यहाँ पे आएगा हमारे पास 1 और 0, है ना। 1 0 दैट मीन्स वो कंट्रोल हमारा जो सा वो शिफ्ट हो गया। कंट्रोल शिफ्ट होने की वजह से वो हमारा तो कंट्रोल बिट हो गया 1, तो उसकी वजह से टारगेट, ठीक है। दिस इज फॉर प्रैक्टिस, अगर आप ट्राई करना स्वैप गेट हो गया। स्वैप गेट इज नथिंग, जस्ट स्वैप द थिंग्स। अगर मैं बात करूँ यहाँ पे देखा जाए कि यहाँ पे मैंने 1 0 और 1 0 कन्वर्ट किया 1 में पहले, बाद में 1 साथ में लगाया, तो वो 1 1 आउटपुट 1 और 0 आउटपुट। यहाँ पे इशू किस किट में एक सबसे बड़ी दिक्कत रहती है, ये जो सा है ना ये वाला, हम अगर 2 पावर 0 से शुरू करते हैं ना बाइनरी में, 2 पावर 0 2 पावर 1 2 पावर 2, तो इसमें किस किट में उल्टा रहेगा, इस किट में उल्टा रहेगा, ठीक है। चलिए, एंड अनदर इज टपोली गेट। टपोली गेट इज यूज्ड फॉर 3 qubits, not for 2, it's for 3. टपोली गेट इज फॉर 3 एंड द रिजल्ट इज दैट इन दोनों का ऊपर वाली 2 बिट्स जो होती है उसका एंड होगा और उसके बाद वो उसके साथ सी नोट करेगा थर्ड वन। और ये उसका विजुअलाइजेशन है कंपोजर में। स्टेट अभी बात होगी इसके बारे में। दिस इज विजुअलाइज कर सकते हैं इसको, इसका आउटपुट क्या। ये नेक्स्ट क्वेश्चन थे हमारे पास 3 qubits पे, अगर रन करने हैं तो मैं करवा देता हूँ अभी।
सर PDF शेयर करा दीजिए।
कोई बात नहीं मैम, मैं शेयर कर दूँगा। एंड वन थिंग मोर, ये देखो यहाँ पे ना बिट फ्लिप किया है यहाँ पे, अगर देखा जाए तो आउटपुट अगर देखोगे ना, ये देखो ये यहाँ पे मैंने क्वेश्चन करा, ये सेम क्वेश्चन करा, ठीक है। ये सेम आउटपुट अगर आपको देखो वहाँ पे 3 0 और 3 1 है ना आउटपुट में। अगर मैं नेक्स्ट की बात करूँ, मैंने सेकंड बिट फ्लिप कर दिया यहाँ पे। सेकंड बिट फ्लिप करने का मतलब क्या है, ये वाली पहले 0 थी, ये 1 हो गई इनवर्ट फ्लिप कर। तो मैंने किया क्या है यहाँ पे, अगर ये वाली जो सी 1 1 थी तो इन बिटवीन वाली 0 हो गई है। मैंने अंडर एक्स गेट लगाया बोथ 2 बार। अगर मैं 2 बार अंडर एक्स गेट लगाता हूँ वो सेम आउटपुट देता सिंगल एक्स गेट। अगर आप ट्राई करो यहाँ पे देखो, यहाँ पे मैंने लगाया सिंगल एक्स वाला, इसकी आउटपुट भी सेम है। अंडर और अंडर को ऐड करके एक्स गेट आया। ये कोई बता सकता है इसके आउटपुट क्या है? सिंपल है, इससे छोटा सर्किट नहीं मिल सकता है। दिस इज फॉर एक्सरसाइज ये मैथमेटिकली आप सॉल्व कर सकते हैं इसको। इसमें हेडामार्ट है, मोर देन वन हेडामार्ट। इसमें मेजरली आपको वो चीज़ पता लगेगी कि हेडामार्ट से एडवर्ट कैसे करते हैं। और हाँ, ये लैब का है, इसमें सर्किट लैब में जो सा आपने लैब का भी ओवरव्यू देखा, सर्किट लैब में कैसे दिखा था।
तो कैसे एग्जीक्यूट होगा ये?
सर ये एग्जीक्यूट सर्किट जैसे हमारा वहाँ पे एग्जीक्यूट हो रहा था
IBM में ये? हो गया? तो query?
कोई क्वेरीज?
सर मेन यही है ना, क्वांटम कंप्यूटिंग सीखनी है तो पहले गेट्स क्लियर हो जाए, फिर ही उसके बाद नेक्स्ट स्टेप हो
गेट एंड पाइथन
गेट्स और पाइथन। ਤੇ ਜਿੱਦਾਂ ਆਪਾਂ C ਇਹਨਾਂ 'ਚ ਪ੍ਰੋਗਰਾਮਿੰਗ ਕਰਦੇ ਆ, ਇਹਦੇ ਵਿੱਚ ਵੀ ਕਰ ਸਕਦੇ ਹਾਂ।
मैम वो पाइथन वाली प्रोग्राम
ਉਹੀ ਹੋਏਗੀ।
पाइथन आनी चाहिए, पाइथन लिखो
ठीक
टोटली पाइथन ये IBM कंपोजर इसको और नॉलेज इन हाउस
ਉਹ ਤਾਂ ਜਸਟ ਹੋ ਗਿਆ ਕਿ
गेट वर्क क्या भी कर रहा है, गेट दी आउटपुट क्या आ रही है ये एग्जैक्ट दी गल करिए, एग्जैक्ट पाइथन।
So just a real problem कोई भी like this सर
मैम फिजिक्स डिपार्टमेंट की प्रॉब्लम यही है
गेट्स वगैरह कुछ यूज होते हैं।
एक्चुअली ਉਹਨਾਂ ਦੀ ਪ੍ਰੋਬਲਮ ਮੈਮ यही है ਤੁਹਾਡਾ ਨਾ जैसे अपने मैम कर रहे हैं ना सर विशाली मैम, ਉਹਨਾਂ ਦੀ ਵੀ यही ਸੀਗੀ ਵੀ ਉਹਨਾਂ ਵਾਸਤੇ ਇਹ ਵਰਕਿੰਗ ਨਹੀਂ ਹੈ ਕਿਉਂਕਿ ਤੁਸੀਂ ਰੀਅਲ ਟਾਈਮ 'ਚ ਕਰਨਾ ਹੈ ਨਾ, ਅਸੀਂ ਸੌਫਟਵੇਅਰ ਦਾ ਡਿਜ਼ਾਈਨ
कंप्यूटर से बैकग्राउंड
फिजिक्स की है,
मैडम जी फिजिक्स की है एक्चुअली ਸਾਡੇ ਉੱਤੇ ਮੈਮ ਹੈ ਸੋ ਸਭ ਵਾਈਫ ਹੈ ਉਹ ਵੀ ਫਿਜ਼ਿਕਸ ਤੇ ਹੈ, ਸ਼ੀ ਇਜ਼ ਆਲਸੋ ਡੂਇੰਗ PhD ਇਨ ਕੁਆਂਟਮ ਕੰਪਿਊਟਿੰਗ ਆਲਸੋ। तो ਉਹਨਾਂ ਵਾਸਤੇ ਵੀ ਇਹ ਚੈਲੰਜਿੰਗ ਹੈਗਾ ਕਿ ਉਹਨਾਂ ਦਾ ਜੋ ਰਿਸਰਚ ਜਿਹੜਾ ਏਰੀਆ ਹੈ ਨਾ, ਕਿਉਂਕਿ ਸਾਡਾ ਰਿਸਰਚ ਏਰੀਆ ਐਪਲੀਕੇਸ਼ਨ ਦੇ ਬੇਸਿਕਲੀ, तो ਉਹਨਾਂ ਦਾ ਹੈ ਨਾ ਕਿ ਸਟੇਟਸ ਕਿੱਦਾਂ ਮੈਨੇਜ ਕਰਨੀ ਹੈ। तो ਫਿਜ਼ਿਕਸ ਦਾ ਜਿਹੜਾ ਰੂਲ ਹੈ ਸਿਰਫ ਸਟੇਟਸ ਦੇ ਅੰਦਰ ਹੀ ਫੋਕਸ ਹੈ ਜ਼ਿਆਦਾ, ਠੀਕ ਹੈ। ਉਹਨਾਂ ਨੂੰ ਜੋ ਅਸੀਂ ਕੰਮ ਕਰਾਂਗੇ ਉਹਨਾਂ ਨਾਲ ਕੋਈ
वर्चुअल लगेगा कि हाँ जरा कुछ कंक्रीट कुछ हो गया।
हाँ ਉਹਨਾਂ ਨੂੰ ਕੰਕਰੀਟ ਚਾਹੀਦਾ ਹੈ ਕਿ ਫਿਜ਼ਿਕਸ ਵਾਸਤੇ ਸਾਡਾ ਕੀ ਯੂਜ਼ਫੁਲ ਹੈ। तो क्योंकि वी हैव बिलोंग टू कंप्यूटर बैकग्राउंड, तो सानू जो चीज साडे वास्ते यूज ਅਸੀਂ ਉਹਦੇ ਤੇ ਫੋਕਸ ਕਰ ਰਹੇ ਹਾਂ ਫਿਜ਼ਿਕਸ ਵਾਲਾ ਸਾਡੇ ਵਾਸਤੇ ਕੋਈ ਯੂਜ਼ ਨਹੀਂਗਾ। ਬਟ ਹਾਂ ਤੁਹਾਡਾ ਜਿਹੜਾ ਕੁਐਸਚਨ ਹੈ ਬਿਲਕੁਲ ਰਾਈਟ ਹੈ ਕਿ ਫਿਜ਼ਿਕਸ ਵਾਸਤੇ ਕੀ ਰੋਲ ਹੈ ਜਾਂ
मैम ਤੁਸੀਂ क्वांटम डॉट्स से काम कर सकते हो, बहुत अच्छा है
आप
क्वांटम डॉट्स
ਉਹਦੇ ਜੋ ਗੇਟਸ ਵਗੈरह यूज होंगे या
ना मैम गेट्स वगैरह कुछ नहीं होंगे, एक्चुअली रियल टाइम एप्लीकेशंस है, फुल वगैरह लेके भी उनको बनाना होंगे, वो क्वांटम डॉट्स बनाने होंगे हर करके BHU कम होया हो मैम
लेकिन और बनाना
फुल गेंदा फ्लावर ना ਉਹਦੇ ਤੋਂ ਕੁਆਂਟਮ ਬਣਾਇਆ, ਕੁਆਂਟਮ ਡॉट बनाया।
So basically ये three dimensions
इंटरेस्टिंग यार, इसका भी गल करना मजा आ गया।
ਸਾਡਾ ਰੀਅਲ ਹੈ ਨਹੀਂ, ਸਾਡਾ ਤਾਂ ਆਹੀ ਹੈ ਬਸ।
इससे डॉट ਦੇ जो डायमेंशंस रिड्यूस करते हैं ना, तो बेसिकली क्वांटम रेंज ਵਿੱਚ आ जाता है।
हाँ जी
तो उसके सारे मींस जो क्वांटम
हाँ वो तो कोई भी हो, मैं सर का लेक्चर सुना थी फिजिक्स डिपार्टमेंट के लोगों के
सारे लेक्चर्स ਵਿੱਚ ना आई एम फाइंडिंग द आंसर टू दिस क्वेश्चन कि फिजिक्स कितने फिट होती है, जब फिजिक्स फिजिक्स कितने
फंडामेंटल तो वही है, फंडामेंटल तो वही है।
It's the 5th day of our FDP, and I request our worthy Dr. H.S. Rai to kindly come forward for felicitation ceremony. Awesome.